Okay, so let's start on this. Ridiculous. Truthicide. Okay, so this is quite, very interesting history of science madness in here. People still publishing papers about this. Wow. Okay, right. So this is going to be about, at base, it's going to be about metabolism of organisms and how that scales with their mass. Right, so an elephant uses more energy, right? Famously, sort of, they eat 100 kilograms of stuff a day or something like that, and destroy 100 kilograms as well. Not the best. Not sure what humans are like. We throw out a lot of bananas, I think, right? A lot of food spoilage. Ants don't eat as much, but there are lots of them. So that's an interesting question, right? So we've got all these tiny little things of a species, or you have not just one species, but all the little guys that weigh 3 grams or 4 grams or 5 grams. They have some energy budget, and so they have to take stuff in just to keep themselves alive and run around a little bit. So how do they collectively, how much stuff do they take? Do they take in more than the elephants at the other end, right? Or is it some magical equipartition thing where the big guys collectively are kind of like the same as the little guys, right? There's some sort of beautiful possibilities here for ecological systems and how things fit together, or are constrained, or may or may not fit together. All right. Okay, so we're going to talk about these guys. Okay, yeah. So as I said, metabolism is sort of the big deal. We're going to have this kind of strange history of measuring exponents for this particular area. It goes back to the 1850s. Will be a tobacco plantation in France. Anyway, river networks. We'll talk about some other pieces, and then we're going to get onto biology. So this is going to be about data. Then we'll get to theories that have, where people have had disagreements with each other, amusingly. All right. Okay, so this is the sort of story we're going to get to. For some reason, 3/4 and 2/3 will be the people involved. 1/12 is the difference between these two numbers, but this is like, my kingdom for a 12th, right? So this is a big deal. This is ridiculous. I want a bunk thing. I did for a while try to make a bunk happen as I moved from slide to slide, but this is just really useless. Okay. I don't know if this is really true, but anyway, scientific integrity system, peer review, which is a disaster actually, of course. People are represented by 2 highly overlapping yet equally important. Oh my God, it's terrible. The independent scientists who review papers and the scientists who punish those who publish garbage. This is one of their stories. All right. Okay, so big range for organisms, and I'll show you that people have tried to connect this down to single cellular things. I guess no one's pulled out the Gaia hypothesis, which would be kind of fun, but they should be doing that. Maybe you guys do. Some of you might know about that, but that's James Lovelock's conception that the whole Earth is one big organism, which I guess is true in Guardians of the Galaxy 2, but that's different. Okay, so here's a shrew. So these guys are really small. 3 or 4, ego, right? Yeah. 3 or 4 grams for these guys, and maybe it's like 3,000 kilograms, 4,000 kilograms. Big units. So very different metabolisms and activity rates. And so there's a very nice thing in here as well, is that, right, these guys eat less, but their heart rates, and they live typically not as long, right? So the bigger organisms broadly, very roughly, live for longer time periods. Things like time to reproduction maturity varies as well in interesting ways. Although it's that said, you can still have a cockatoo that's 110 years old and repeats what your great-great-grandparents said, which usually is the profanities. So, they're not big. So this is a shrew. This is an elephant shrew, which is a very confused animal. Or our taxonomy. Yeah, anyway. Not such a big thing. But this is the big story, right? So that the basal, and I'll call it P, it's different things in different, in the literature, basal metabolic rate. So this is if you're sitting down, just taking it easy. So that's a problem with testing, right? So you can't have organisms running around. There's some beautiful stuff for, and we had this in pucks, for maximal efforts. So there was a scaling result, right, which was that maximum velocity scaled as length of organism, which was true for aquatic species and land species, so it was pretty cool. Usually the maximum, a thing going as fast as it can, which is only for sort of 10 seconds for a lot of organisms, maybe, they burn up all the energy just sitting there waiting for go time. That seems to scale more like mass to the 1, right, using everything. Weightlifters, right, that result, that's more like mass to the 2/3, and the argument there is it's more like the cross-section of your body, right? So that's the maximal scaling. That's within humans, of course, within one species. But here we're going to go across many species, and the question is, what's this scaling, right? So if it was 1 is kind of the upper limit, that's fair. It shouldn't be greater than that, otherwise things would not be working very well. And you would think for a resting thing, the lower the better, whatever you can get away with, right? And of course, specific organisms take this to strange limits, right? We have sloths, which are super cute, and sleep like 23 hours a day or whatever it is, right? They run on not much. There's a super cool rodent, which is I think the Arctic squirrel, maybe in Alaska and Canada, which can get its blood down below freezing because is that right? It doesn't have, essentially has antifreeze, like the crystals can't form in its blood, which is, so there's a lot of adaptation. There are, of course, hibernating animals and all those sorts of things. Reptiles, right, which don't heat, they don't heat themselves, so they potentially have different scalings. And birds make for another thing as well. So we'll talk about these. So there's a prefactor. Often, physicists and many people don't really care about that. Physicists, I should say. A lot of people do. But the prefactor C seems to matter a little bit. And this is the ordering that kind of makes sense. So birds at the top, right? So birds are, latest bit of evolution in some ways, right? Had to have some dinosaurs beforehand, but they're doing a pretty difficult thing, and they burn a little more than mammals do. So this is us, the placental mammals, right? So we have the babies on the inside, or we bake them for a while on the inside. So eutherian mammals, we tend to have this kind of body temperature. I'm using Celsius for just. It's an aggressive act, I realize, but Celsius doesn't make sense anyway. It's ridiculous. All right, marsupials, right, with the pouch, right? So they put the baby in a pocket. So they, evolve in a different line, and it's sort of, and this seems to be kind of the story is, the argument is that that they're sort of just doing like flying is the piece here. This is the babies on the inside. This is babies in pockets, and they don't have to run as hot. I don't know if that's true, but they do seem to have their own prefactor. And then the monotremes, of course, great organisms in the mammal world. So these are mammals plus birds. The platypus and the echidna, right? So these are the only two running around. So these ones, they lay eggs, right? Which is just great mammalian action. So these two are cousins somehow. But anyway. That's the Australian porcupine, basically, and it does the porcupine type things. It doesn't care about you because, literally bite me, right? Okay. Although I think porcupines are much more, they just don't care. It's like, it's just not a possibility that someone will try to eat them. Humans are very clever, though. Okay, so, anyway, so these guys seem to have a lower temperature. But I don't know, the variation, like how many, like platypuses and echidnas, there's not a lot of, when it comes to exponents, these are, I don't think there's really a scaling that you could get out for these. There's not enough variation in body size. All right, anyway, interesting thing. Okay, so this is what you might expect, dimensional analysis. You just, you get your envelope out, you don't even really and then you put it down because you don't really need it. So you'd expect that you've got a heat balance issue, and you're giving off heat, right? So this is why the military can find you in the middle of the night, which is unfortunate, because you light up, or at least on TV, but it is true actually, right? You've got infrared and you're giving stuff off. We complicated things, right? So we give off heat in various ways, and humans are good at sweating, right? When we run a little, when we work harder, which is not what a lot of other organisms do. Dogs have to deliver it out the front with the tongue, which is just a difficult maneuver. But they're always happy, so it's okay. So it might be proportional to surface area, because regardless of sweating and all those sorts of things, everyone gives off heat, right? Infrared. So surface area, we're going to assume spherical organisms, but not really spherical organisms, at least organisms that scale isometrically, right? So snakes are not in here. So this is volume to the 2/3, which density, assuming density doesn't change too much, the density of a shrew is similar to the density of an elephant. Obviously these things, but it's not going to scale in a way, right? The density will change, but not dramatically. So that you would have this 2/3 scaling. And so that's the old idea. So we'll just get to so not quite the spherical cow, yeah. You might expect log normal fluctuations, right? So that if you had some big scaling law and you've got all these masses here and there's some variation around it, of course, that if we look at the residuals around that scaling law, we'd get a normal distribution. It's in log space. So that's nice log space, log 10. Lots of edits. So we have a normal distribution, and that will be good, right? So that's fine. And then there's again, we reach into the big box that says physics, and we pull out the Stefan Boltzmann Law, a very famous result, which is that if we've got a black box, some shape, this is a different kind of black box to the problems we have now, but this is it's radiating, it's giving off heat, it's absorbing as well, but it's giving off heat. That the way that that happens, the rate at which that happens is proportional to surface area, and then temperature to the fourth, right? And so we'll think temperature doesn't matter too much, right? Here we're not going to vary too much, but surface area is the big story. So it would fit, and this is an old argument, right? This is sort of the first argument that people have. And then, if you're working harder, you have to cool off in different ways. But actually, this is what people think, right? So it's now people have thought this from the 20s really through into the 2000s, but there's a lot of, then it just exploded, right? No one had a theory for it. A theory comes along that purports to explain it all, and then everything explodes. So we'll get to that. But it turns out the data supporting this is not good, and that's going to be the first place we'll get to. So 3/4. So that's pretty weird. It's pretty strange. It's a difference of a 12th. It's higher than 2/3, so that means that biology is perhaps forced to produce organisms that run a little hotter than you'd expect based on scaling. Maybe they do for larger mammals. That might be true. Really getting bigger, gravity battles out of interesting ways. Somehow they run a little hotter than they need to balance heat. All right. So I'll just finish with this sort of beautiful thing, and then we'll go into it. And so the actual exponents perhaps doesn't matter here, right? But let's just believe for a little bit. There are various claims associated with it. So the number of capillaries that we have scales as mass to 3/4. So that matches with this idea of energy usage, because you're sitting there running, and that's where the little engines is where things are happening. Mitochondria might be another piece in here as well. People have measured that for organisms. Time to reproductive maturity. These are all incredibly rough things. You can see that someone's come along and made them into fact, but a quarter power here. So it's a slow scaling, but it's growing. Heart rate decaying, right? So bigger things have lower heart rates. This is true, and as you grow actually, right, your heart rate goes down. Cross-section of the aorta is another claim, right? So obviously lots of aortas being cut up and looked at by people. Mass to the 3/4. This is so-called Damas law, population density. Wow, I'm going to add that one. This is a long list of nature and science papers as well, Damas law. It's known as Damas law. There are a couple of pieces that fit very nicely. So population density times the metabolic scaling. If you put mass to the 3/4 times mass to minus 3/4, mass to the 0. So that is this kind of idea that organisms of different sizes consume the same amount of energy, right? There are fewer of the, and it's more than that. It's per unit area, right? So there are fewer elephants. They're spread out more, lots of mice. But when you look at how much energy they use per unit area, it's the same. That's a claim. This is all claims, all claims. This is quite a beautiful thing. But let's say lifespan grows as mass to some power, average heart rate goes down. Then you multiply those things together. And this actually does seem to be roughly true, right? So it's about, this is a beautiful idea, right? This is a beautiful idea. People write poems about this. They get very excited. It is roughly on the order of 1 billion and a half heartbeats per organism, right? That's what you got. So if you're an elephant, just run it, the whole thing runs slower, yeah? And if you're a mouse, you're just hammering through the clock. So whether a mouse thinks it's basically living the same life as an elephant, I don't know. I'll see if I can find that poem. Okay, yeah, 1.5 billion. Okay, so this is what we're going to talk about, the Church of Quarterology. This is an interesting thing. And eventually we'll get to how does this all make sense, and beautiful theories that are wrong, and beautiful theories that might be right. Okay. All right, this is fun. Yes. And office hours will be over now too. I'm sorry, that's just super interesting. All right, okay. So we talked about optimal sporks, and then we're going to talk about this thing. Church, we should have sporks. Church of Quarterology, right? And so this little ridiculousness is 3 divided by 4 is what that piece is. So this still goes on. I was looking up more stuff last night, talking with an old friend about the stuff that's come out more recently. Anyway, let's talk about it. Okay, so this is back in the 1840s. It was thought to have been a published paper. It's sort of not quite. There is a document you can find, and I'll... oh, sad computer. What have I done? Well, while it's thinking, possibly... Okay, so I can escape. That's important. Oh, wow. Okay, I'm just going to crush this thing. So that just worries me. Force quiz. So the best thing is kill all, but this does work. That's good. Okay. Okay, so what's happened? So this is 1840s. It's a tobacco plantation in France, and they are worried. The people running it are worried about how much to feed people, right? So they think, maybe we should feed the bigger ones more, right? So fair enough, and maybe. So, but how much more? And so they went to a local, and I can't remember the details off the top of my head, but they went to a local. There we go. They went to a local, they found some physicists, and again, this is 1840s, science is sort of just taking off, and asked them, how should this work, right? If we have someone who's, 1.5 times as heavy or tall or whatever, how do we do this? And so they suggested this exponent of 2/3, right? So the amount of food you should put on their plate in terms of volume should scale as mass of the person to 2/3. And this was this surface area idea, right? So that they kind of you lose heat, and we think of all these individuals as spheres. They're not, but at least isometrically growing shapes. And so the scaling of the surface area should go like mass to the 2/3, right? So it's going to be d minus 1 over d, where d is 3 for the dimension we live in. All right. So that's the. And this becomes something that people look back on and start to cite and point to and say, oh, this is how you should do this, right? So obviously not a great time to be in a laborer, shall we say? Like, this is not good. Things were pretty bad. And I guess they cared enough to give you food. But anyway, terrible times. All right, so 1883, we have, this is actually a formal paper. It's a German scientist. Rubner experimented with dogs, and this is not, no one's doing anything terrible. It's just sort of looking at seeing how much oxygen they use and so on, right? So various kind of tests like that. And this is all, again, at resting. This is a resting thing. So if you've got this organism resting, how much does it use to run at that base rate? And I think I added this. Let me just, I threw this back in here. This is a really nice thing. And this is, again, from Pox. I just put it in there. But this is the scaling of the maximum velocity. This is connected to, like, when something's going as fast as it can, what sort of power does it have available to it? And that tends to scale as mass to the 1. I mean, this seems to be a rather remarkable result. I mean, that's a huge variation, not just in size, but also in type, right? Because we move past, I mean, here we have insects and so on. We're moving through different kinds of biological organisms. But there is a discrepancy between, it seems to be between, is that true? No, they're just putting all those plots there. Anyway, pretty amazing. They have running ones and swimming ones. Yeah, awesome. Then there was a paper that came after that that showed that, in fact, the largest things never really get going that fast because it just takes them too long to get going. And it's a really nice paper. This is a beautiful thing. So it's good scaling, but once you get up to the biggest ones, they start to, like, wind it up, but they've used up all their energy, essentially, by the time they never quite get to their maximum speed. So if you juice an elephant, then it could go faster.
Did you kind of see that in the previous figure?
There's a little bit of a downturn. Yeah.
Get more efficient.
Yep. Maybe these points down here.
I feel like the line should go
Yep.
a little bit. Just like one point way out there.
So this is one of these games where there's 22 orders of magnitude here. There are 2, which is not usually that's right. I mean, that's a decent range, but for this paper, it's like, look, amazing. And this is a really beautiful treatment to show this kind of upper limit problem. And usually there's something that happens at the ends that's absolutely fine. They just really explained it beautifully, right? So this is the plot that came with that. Right, so this is how much time it takes. The elephant is getting going with the whole 4 knees thing, which is pretty unusual, and it just doesn't quite, Awesome. Elephants are cool. Okay, so that's an extra piece, but I just want to say. So we're talking about resting metabolism. So looked at dogs, found that it made sense. Alpha is again 2/3 for the scaling, right? And so the scaling we're talking about is, this is going to be P. Oh my gosh, why would people? Okay, so I'll deal with that later. And then, okay, not bad. Mass to the 2/3 was this idea, but this is alpha, right? This is early on. So all right, let's leave it as the who knows what's going on business alpha, right? Okay. But basal metabolism as a function of mass. So then in the 30s, I guess we're okay with humans by this point, but people are worried about livestock, right? So they want to know how much to feed livestock, based again on size. Things are becoming more efficient. Eventually we get to McDonald's where all the potatoes will have to be the same shape and so on. But people forever have been trying to make agriculture and animal industries work better and better. So this is sort of part of all of that. And they found a bit of a variation. So this is work by Brody, which is often pointed back to. Benedict's as well as a different paper, where they find a higher exponent, it's 0.73. So it seems like organisms are running a bit hotter, right, than you would think. What you need to keep a machine going, this biological machine going, seems to scale a little bit faster than what you need to just keep it balancing radiated heat. And this is here because they did some funny things in this data set. So Brody, for example, maybe has 100 animals, but there are a lot of sheep and a lot of rats and all sorts of things. And some of the data in these points is actually generated from a formula, and then it's regressed. It's really a mess. It's really kind of horrible. It's really horrible when you realize what they've done. It's fine. It's a mess. Everyone's doing messy things. But this is a serious business because a lot of food goes into livestock. Nowadays, dog food people are worried about this, right? dog food companies and cat food companies because they think about this, but also, say, medicine, right? So if you have something that works for a mouse, how do you scale that up for a human? That's a difficult problem, right? You don't just do it's like it's not just weight divided by weight. If there's some sort of scaling in there, you'd really like to understand it. So this bit of hay here, this photo roll, is because you can see Benedict just says they went to a zoo and got hold of an elephant and tried to measure how much energy the elephant was using. I can't remember what method he used, but because it was eating and carrying on, and they couldn't stop it from doing that, because they would actually starve animals to kind of get them to sleep a bit. So I mean, because they needed to be resting / starving. You just sort of see it in the text. It was like, oh, we just deducted 10% from the thing just to sort of account for that. So it's pretty rough, is what I'm trying to say there.
For the animals or for the calculation?
It's rough for everyone. It's rough for us. It's rough for them. Animals, absolutely. Yeah. I mean, I grew up on a farm. It's not great. It's not a great situation. Well, it depends on the people. All right. Hence Animal Farm. Right. So, okay. So this is really interesting. People are very invested in this. As I said, it matters. So then there's this very paper that becomes incredibly famous. It appears in 1932 with Max Kleiber, and he becomes famous for this. This is he has a book called The Fire of Life. This is a big deal, right? We're right. This is a kind of extraordinary thing. I mean, by this point, we've made, engines that do all sorts of things, but we run around doing stuff. That's pretty weird. Anyway, but this is just 13 mammals. It's not 13 species, right, with averages or something. It's like 13 individual, because it's not easy to do. So it's 13 individual organisms. And he ran a regression through this and got 0.76. It's a straight up regression. We'll talk a little bit about regression. As we've seen, measuring power laws is not for the faint of heart. And I'll show you some stuff that we did a long time, and I still think it's fine. Obviously, I'm talking about many people's work, but Kleiber's law. So it becomes known as Kleiber's law. It's still called that. Here it is, the Fire of Life. That's 1961. Kleiber ends up at Davis, actually, right? He's originally from Germany, I think I have that right. And he ends up at Davis. So let me see what this looks like. Yeah, here it is. This is back when you had to go and find a book and go to a photocopier and photocopy it poorly. So it's this sort of thing, right? I mean, this is where we are. This is 1932. So and one thing about this is you can see how much this thing has been looked at, right? And so back in the day, I sort of discovered, so here's Benedict being talked about and so on. I discovered this, like I would find a reference that seemed important, and you go and find it in a library somewhere. I had to find one in the Harvard Medical Library, and I don't know if it was because I was at MIT, but there was a sort of sense that you had to kind of walk in like this, and they didn't really trust you, and there was someone watching you the whole time. Anyway, went to, you find that, how you search through, theoretically, I guess you do. But you just searching through libraries was this thing we would do, and you would have to, match the numbers, find the place, and it's this nice thing, getting closer and closer, and then you find it. And this is a couple of books I'll mention later on, but it's like these 2 little volumes, and you see them, and you see they've just been worn down, right? Like these things have been pulled off the shelf over and over again. Everything else is pristine around it. So you start to get this sense of this is some thing that, as people are just really into this. There's some big universal truth, amazing thing here that the Druids knew about or whatever. There's some sort of feeling of what's going on. Anyway, so does he even have a slope in here? Oh yeah, there he does. Yes, it's on its side. This is my bad photocopying. There it is. They just put it on the slide. Yeah. So it looks pretty good. This is so great. Look at this. It's just handwritten, right? Log M, calories. And that looks pretty good for a straight line, but we'll talk about this. So it turns out, and what I'm going to tell you, is at least for mammals, there seems to be a break in scaling. I mean, there's just not enough data here to be sure of anything. But yeah, a couple of birds. Oh, it's got birds in here too. I forgot about that. So this is a mixture of birds and mammals. Wow. Amazing. Okay. So this paper, this is the core of where this whole 3/4 thing comes from. And it's a lengthy paper. Eventually there's a book, tables, it's so much fun. Wow, this is just terribly done by me. Wow, so great. Anyway, just really enjoyable. Slide rule. So why is there a slide rule? The slide rule is there because at this point they're starting to think it's not 2/3, it's something a bit higher than that, and we want people to be able to actually calculate things. The thing people have handy for doing somewhat more complicated things at that point is a slide rule. And if you're doing powers, you don't want to use 4/7 or something. This is not great. 3/4 is it's a Pythagorean ideal. It's the next thing up that's pretty easy to work with. It's a nice fraction, not too bad. But it's 1/12. But it really is about, and this is, he talks about it. He says, the recommendation is to not use 0.76 or 0.73 because I'll show you some very soon. I'll show you some of this. People are really arguing about this. They want a universally accepted number, right? Which is what we would like in science, right? We would like that. But they're pragmatic people, so something strange is going to happen. So first of all, 3/4 because that's easy to use. Okay, rule of thumb. That's fine. It's a bit later. These are the books that I found that are really, these are these weird books that I found at Harvard Business School. Wow. And these are just sort of little booklets. It was written by a guy who worked at a hospital. I think he was a doctor. And they're just these little booklets. And now we've got everything. There's insect eggs, bacteria. There's trees in here somewhere. Poikiliotherms, which is cold-blooded organisms. Unicellular organisms. So this becomes the reference now for, and so here are the two slopes, right, of 1 and 2/3. This becomes the citation that people use for saying that this is true for not just mammals or birds, it's true for everything, right? If you can somehow go down to unicellular organisms, or you could do it for trees, everything. Okay. But it's really crazy. So this guy does all sorts of odd things, including just presuming it's 3/4 and then fitting the intercept. Like, it's a done deal by this point, right? It's just like, I'm just going to find because that's, and that's sort of interesting, right? I talked about that before with birds and different kinds of mammals. That's sort of an interesting thing. So you can see that's happening in here. This is so great. This one, has it got more good things in it? There they are. And he's just reproducing data, right? This guy's like a kind of a fan. He's having a great time. Lizards and snakes and alligators. Just imagine someone has measured the energy usage of an alligator. Or some graduate students were going. But Morris didn't come back. Shut up. Just going, don't ask questions. So that's fun. You can go and look through these things because they're sort of very interesting artifacts to me. Okay, so this, and if you read through, as I said, assumes 3/4 is true. Did a lot of stuff with mold. This is a mold with a very bad name. A lot of people spend a lot of time studying slime mold because it does really interesting things, but it's just sort of like, it's not a charismatic organism. That's a problem with slime mold. It's super interesting, make lots of shapes, but it just doesn't have the cell. Anyway, yeah. Okay, so how about this? This is pretty great. So this is a right. So it's a symposium. It's a conference, and they actually have a vote. They have a vote. They really have a vote. They vote on what the official exponent should be, 29-0. And you can. So I have this book. There's actually a transcript of the meeting. And at some point, someone goes off on some tangent where they try to explain why it's, 2/3 or something else, but they absolutely get things upside down. You can see that they do. Mathematically, they've got things upside down. It's a disaster, whatever. And then basically, you just sort of see all of their discourse, and then whoever's in charge says, well, thank you very much. And then they just sort of go back to, it's like, you can imagine some mad academic spouting some stuff, and they're like, thank you, Henry. And then they're sort of back into their discussion, and then they have a vote, and it's 29-0. So this is science. Science. And that's what I see. So the cabal slipped up because they actually published the conference proceedings, and you can read their silliness. Oh, I should scan that. Yeah. Scan silliness. I don't think I did that. Did I scan it? That was dangerous. No, I didn't. But I do have the book. Yeah. I was going to scan maybe a bit of it. Yeah, there you go. Yeah. Troon, Scotland. Very good. So, because it matters. I mean, people are worried about it again for feed, for lots of different organisms, livestock and so on, but then aspects of toxicology, right? How do you scale things up? And so on. But really weird, really weird. So you will find, certainly this is something you find in biology textbooks. It's just written out as a true thing. Now, I've shown you people's just analysis of data sets, right? And they're sort of moving towards this thing. There are no mechanisms here, right? No one has any reason for why this. There is this old one, the simplistic one from the physicists, the very simple one. And we'll see that you have to kind of go further than that as well when we come back to it. All right, the truthicide. Okay. Sorry, I'm amusing myself. Okay. So what happened here, right? So this is all this sort of silliness. Is this really dead, right? So I'm sorry. But this bottom one is quite serious. Like, who votes on scientific facts? I guess we voted Pluto out of existence. I guess we do those sorts of things. But numbers, that's not right. We did the pi thing. The pi thing. Are you going to say that? Yeah, that was in Indiana, I think. Someone wanted pi to be 3.2. It got a fair way, right? It was a local government thing.
Yeah, they had a mathematical proof of it.
They were worried about circling squaring the circle or whatever. A lot of these things, like it would make that easy, I think, or doable.
You could square the circle really easily.
That's real. I mean, look, some of these things in the past just really are funny and absurd. But I mean, the history of science is full of madness, right? I mean, but a reasonable madness at the time in some ways, because we had no idea. But that seemed, that just seemed very silly, yeah. Because, the pi thing we kind of like got into for a couple of thousand years by that point. Oh, they got a long way into it, yeah, because he.
And then there's
a good story.
Mathematician who was like sitting in for some other court case, and I was like, this can't be.
So great. Also, I was thinking about this. So Pluto goes. What about Brontosaurus? Are you allowed to say Brontosaurus anymore? Or is that just not cool? It's a Patasaurus, right? Yeah. That's so sad. Why did we vote that away? That's not a thing? Wow, that's disappointing. Or is that just the whole thing where they're trying to make a bigger one? Is that fake dinosaur stuff? Oh, you mean like it's a miniature version? Oh, no, it's the infants, or the whatever the infants is not the right word. Yeah, okay, the juvenile version. Damn. Yeah, no, that's all madness. I mean, that's fair enough. We can. But when I was a kid, right, the stories were the Triceratops and Tyrannosaurus. That was the big deal. And then Velociraptors. We never had Velociraptors. I felt cheated because they're pretty cool. Okay, right. So what's going on? So journalists wrote about this. This has been sort of repeated. I'll come back to this one a little bit later on. This is a book that appeared around 2000, and it's going to be based on this theory that I'll talk about later on, and I know I'm just enjoying myself here, that comes around. So no one really figures out anything until just before 2000, right? So there's a paper in Science in 1997, and that will be something we'll get to. That's covered in this book. John Whitfield was a writer for Nature. And he talks about it in sort of glowing terms, Kleiber and all this. Right, everyone loves the elephant mouse thing. This is sort of fun. So we're gonna, we have some work, but there's an explosion of work around this. But I'm gonna point to a couple of things. But I'll show you much other stuff. Anyway, we got ourselves involved because of this network stuff. Dan Rothman is my advisor, who's at MIT. Still, he's in earth sciences there. He's an applied mathematician kind of guy. He's done some really cool things over the last 20 years with the carbon cycle and how life, actually just the expansion of life had sort of changed the atmosphere. And he has work now about extinctions, so it's not fun. Like when the next one's coming, like how things are working statistically, really detailed, deep work. And Josh Weitz is went from physics to biology, is at Georgia Tech, super guy. Yeah. Anyway, this really did feel like one of these, it was just an incredible sort of amount of work we had to do to figure out what's going on. So here's some data. This is data from Heusner, so this is a meta study, right? So meta-analysis, so he's gone through a ton of papers. This is a really well-done paper. And I want to say some more things about Fred Heusner. So Fred Heusner. So he goes, and he does it for birds and mammals. This is for mammals. Puts together this really, really well done paper, because at the end it has every reference, it has every data set, and all the numbers are there, right? So it's really great effort. So this is pretty weird. So I remember getting what he kind of did was he claimed that it was really 2/3 and people were making a mess of this. And the story that he had was there was just something weird about these larger mammals, and that there were really like two slopes. Like you had to kind of think of these as a different thing. He had a sort of statistical argument analysis that said, you really should discount these. And I'm not going to go into that too much. But the thing is, I remember getting the data, because it's just sitting at the back, so I just typed it all in. And we were driving down to the Cape, actually, and I've got this like massive Toshiba thing, and I plotted and just did a regression. And the thing is, if you just do a straight-up regression, you get 0.668. So this is really weird, right? So I'm like, what is going on? This is so strange. And I'd sort of got, I'd obviously reading this paper, which is talking about it being 2/3. It seemed to be this big rebuttal, kind of piqued my interest. So we're trying to figure out what's going on. And 3/4 is this red line. This is in no way proves or shows that it's one or the other, but it's a weird thing. So how do we get to this, right? So we've talked a lot about the river networks, the branching network stuff. There's a really pivotal character in here, Jeff West, who's a very famous guy. He's a theoretical physicist at Los Alamos, but he ended up working with people at Santa Fe in the Santa Fe Institute. He became the head of that institute. And so his work, with a couple of others, will be the core theoretical work that. Here's the thing, by that point, 3/4 was just true, and the game was just to prove it. And then you get a physicist who will do that, which is fun. It is, and it's sort of shocking to go back to the data. Like I think I talked about in scaling last semester, there's a quarter power scaling for the number of species as a function of island size, right? And that's this kind of cool, MacArthur, I think, was the paper in the 50s. And it's a quarter power, right? And I've seen papers where they prove it. They just show, they've got a little model, the number of species increases as area size to the power of a quarter, and they make a little sort of charming little model that does that. It gets a quarter exactly, right? And there's some story. But if you go back and look at that data set, it's just a horrible mess, where there's just sort of a line just smashed through the middle of it, and it's just sort of, it kind of goes up, and it's not linear. But the thing is that doesn't get seen, and that gets, and back in the day, it's a little hard, right? Because you had to go to a library, right? You had to actually have access to that book. That's different now. Like the photocopying thing was not fun. It was not, you sort of put it down, put the thing, put it down, and eventually you just give up, right? You don't close it anymore. You just like, it's just like, it's terrible. Exercise. Okay, so this one is, and this is birds, right? So this is a really interesting one because with birds, it's like super duper 2/3, right? It's 0.664. There wasn't sort of an extra piece up here. So how did people cope with this, right? This is close to 400 birds. it didn't fit this 3/4 thing because people really believe this by now. They just think this is true, and it's a magical thing about biology that no one understands why, right? No one understands why. That's 1987 that Bennett and Harvey done. So what happens around that time when people start to look at birds is that they break them into perching and non-perching birds. So this is clever, right? So the idea of ostriches are not perching birds, for example. So you have, so then the idea was there were two kinds of birds, and they both had a 3/4 exponent. That was the little game, right? So that's the solve for that one, right? It's total garbage, but So it turns out Heusner and Kleiber were both at Davis, and they're a generation apart. When I was sort of looking at this, Kleiber had passed away by that time, and I managed to actually call and talk with, this is a long time ago. Email existed, of course, but Twitter didn't. And I spoke with Heusner. It was interesting to talk to him. He'd retired by that point and was making pots. That's what he did. He made pots, and he would sell them and stuff, and he lived in Davis, and he was having a good time. They were both from nearby, actually, in France and Germany, and they both ended up at Davis. And they became family friends, actually, right? They would go on family vacations together. And this is, just me talking to him, finding this out. And they were very close friends. But Kleiber's sort of whole career was about this 3/4 thing, and then Heusner, for whatever, he works on this stuff too, and he looks at it and he's like, I don't think it's right, it's no good. Publishes papers that are, and he kind of published some of it after Kleiber passed away. But he told me that Kleiber sort of, at least to him personally said, it's righto, it's sort of a mess, and kind of agree with him and so on. But it's kind of an interesting, sad thing in there, that these two people had this, they got along, actually, they got along. I know that Heusner told me that West came to speak at Davis and was just kind of really abusive to Heusner, which is terrible, West is an interesting character. He's English and has a very deep voice, and that gets you a long way in the world if you want to colonize sciences. Anyway, what can I say? That is my weird heritage, I suppose. But I come from not England, but a part that came from England. So by obligation, I must hate them. All right. So there are lots of good people. It's fine. But it's like you must make jokes about the English, and you're very happy if you beat them in cricket. Any sport, actually, because they invented most of them and then are terrible at them, especially soccer. Anyway, no. So the other thing is, though, no, I've gotten along quite well with West. So that's not the issue. But it is very controversial, though, and it's kind of a weird thing because, and I look at the world of fake news now. You really do have scientists who just stick to it. They just say, no, it's true. It's true. Even though you can mathematically show that their mathematical thing doesn't work, people don't read these things properly. It's really true. There's a lot of stuff where people do not go into the details. It's very painful to do that. And it always gives me such hesitancy about any major, messy scientific thing, But, yeah. Okay, so, looking at this, you're like, this is crazy. What is going on? And I'll tell you a few, let's just do a few measurements. So we can do ordinary least squares, right? So that's you've done this a million times, I'm sure, but it's a simple thing. Wow, the sadness. Okay, these have to be eliminated. Okay, so here's the thing. With ordinary least squares, we've got some y, we've got x, we've got some dots. And what you do there is you assume error is in this direction. Right, this is a very important aspect of this thing. You can regress x on y, and when you do that, you assume the error is in this direction. Now, it may be that you really have errors in both, right? And that's often the case for things. So then you kind of want to assume some sort of error ball for both of them. And that's a different mathematical thing. You may be able to characterize the error in some way, so then you take that into account. You may have no idea, and there are different treatments for that. So I just wanted to, it's called major axis regression. There are different kinds of, or reduced major axis regression. I want to show you this. It's quite a beautiful thing. So it's a little bit of a detour. But we would certainly, if this is mass and this is something like metabolism, mass we can measure well, right? So we're going to be happy about that. Metabolism, much messier. So it's going to fit into classic regression. Okay, well, is that true? Okay, ordinary least squares is a good thing. So standardized, I guess it's now called standardized major axis linear regression. So that's what you do if we don't know what the errors are, right? So it's just a big mess. And I want to point you to, wow. So Samuelson, who's a famous economist, has this 1942 thing that I would point you to. And then there is a paper here, Rayner. This is great too. This is from zoology, right? Completely different worlds, right? But this is all about regression and thinking about the different kinds and connecting them in cool ways. So, but let me just show you some of that. RMA, right. And it turns out that this is really this is a surprising thing. It's just this, so we're going to have this, if we take this set of data and we look at the distribution of y, maybe it's like this, whatever it is. Messy thing, right? So we're going to take all of these points and then make a histogram. Like ignore x and make a histogram for y and a histogram for x. There's some standard deviation for this thing, and there's some standard deviation for this one. That's sort of the typical width of this, So the crazy thing is that you actually just, to find the slope of best fit using RMA it's just this standard deviation divided by this standard deviation. And there's a very nice thing where you can connect it to the slopes you get from normal regression. It's just multiplying this slope by the correlation coefficient or dividing by it, right? So there's some details we could go in. So if the correlation coefficient is 1, right, we've got a beautiful thing. Then all of those things match, right? Y regressed on x, x regressed on y, and this one that's in between, they're all the same. Makes sense. So that's in here too, I think. It's the only linear regression that's scale invariant, and that seems unbelievably important, right? And that's what, right, that's weird, right? So that's what Samuelson was thinking about. It says, these things this slope shouldn't matter what the units are, and apparently it does. So Samuelson, and of course, independently discovered by others, which is the, what's it again? Stigler's law, right? That you discover something for the first time, it will not be named after you. So, including Stigler's law. Right. Okay, so this is kind of a beautiful thing. So if you're messing around with this sort of stuff, this is something to know about. Really good. And let me get the Rayner one. Yeah, again, one of these things. So I won't go into too much, but this is kind of giving you this idea about the different kinds of errors. So this is exactly the thing I was talking about. What's weird, actually, is if you do this regression on just a cloud of points, it will tell you, right, you'll still have a standard deviation. It will say that it will give you a slope for that, right? You've got a box of just static noise. The RMA one will just say, okay, divide this standard deviation by this one, that's the slope for it. Because the correlation coefficient is 0 in that case, then you'll get the right thing. You'll get that the slope's infinite and 0, depending on how you regress. Anyway, this is an old paper now, but it's nicely done. There's some good mathematical work connecting all of these things, right? And that's sort of the key thing in here is here's the slope, or the correlation coefficient is connected to these standard deviations. Maybe I said the wrong thing. This is kind of the plot I wanted to get to, right? So here are these different things, right? This is y regressed on x. That's x regressed on y. Is that? Right? This is where you have a conception of error. Here and here, there are ones where you want the line such that, and this is major axis, such that the distance to that line from every point perpendicularly, which sort of should make sense, is as small as possible. I'm not sure what that one is. This is where you want to minimize the area of that triangle. That's what that's what this regression does. So it's groovy, very groovy. I like that a lot. Okay, so that's cool. And this is the thing where the slope, ordinary least squares, y on x, x on y, they're connected by the correlation coefficient, by that factor. That's cool. Okay, right. So that's sort of just a little detour into measurement. As we know, it is a hell space. I have to eat sticky sweet things. Here's a thing. Okay, so I know this. I presented this work at SFI in 2000. You know, it's all good. I mean, I'd met Wes before, and we'd talked a lot, and we'd had a lot of. I'd actually been there to try and work with him. So, but I'm presenting like this is not working, guys. It's got 3,500 citations. So it's a yeah. Our work has got about 500 citations, which is totally fine. It means it exists, and it's people are familiar with it. But it is hard for things to catch up. Okay, and his quote when we showed this, "I don't like statistics." Oh my God, unbelievable. So, but he's changed a lot. Now he thinks data is their biggest contribution, which is the stuff they did for city scaling, which is really Louis Bettencourt. So. What you could do is say, okay, evolution is producing bigger things, so let's kind of look at how the scaling works as we made bigger and bigger things. Of course, things get smaller on islands and there's that sort of stuff, but evolution has sort of opened up this envelope of size. So there are a lot of little critters out of our 391 that are less than 100 grams. And if you do the regression there, and you'll get these exponents, right? So this is within error, certainly 2/3. It's not encompassing 3/4. I guess I won't get through all of it, but I'm sort of going to sort of show you sort of a somewhat careful attempt to do these regressions rather than just sort of put a big line through the whole thing, but just sort of see, does it hold up in smaller parts and so on. So we're going to open this window up as we go to, right? So we're including bigger and bigger organisms, and you can see how the numbers go up. And so this exponent, very close to 2/3, very close to 2/3, certainly with the error. Still good for 2/3. Now it starts to fall apart a little bit. So it's these larger ones that are kind of tugging the thing up. And they may well be different, right? Because we're starting to get to elephants and things, and they have to cope with gravity and in ways that your little furry creatures don't. But there are a lot of things running around on the Earth that are, back in this category. And certainly for birds, so if we do the same thing for birds, which is here, then it doesn't really ever deviate from 2/3, right? So big error down here when we've got 160, and then it's going up. I mean, this is 2/3-ish. It's crazy, so weird. So 100 kilograms is going to be an ostrich. Yeah. And what do we get up to? Yeah. So elephant. There's one elephant in this data set, but it's they're big units.
Has anybody ever looked at density of animals? Because don't birds and smaller animals have a lot of
Birds definitely have a lower density, yeah. So the presumption is for these groups that the density is similar across them. So when we say mass, we also mean volume. I'm sure someone has measured that. I mean, there's every. Maybe I mentioned it, but there's a paper that I came across somewhere where for a number of organisms they had figured out the total amount of mitochondria in the organism by sort of, removing life from it, but also burning it in some way. Like there was some sort of thing that got titrated out the mitochondria. Something happened. It was like the charred remains, and then there was a little sort of pile of mitochondria. It felt like that. There's also blood volume. This will come up. Incredibly, there are papers that appeared in Nature and so on that had blood volume scaling as mass to the 4/3. Just thinking about that for a second, right? So if blood volume is scaling as mass to the 4/3, it's not going to work out, right? I mean, it's okay for the mouse, but once we get up through a few orders of magnitude, it's not going to fit inside, right? So, oh man, this is a really strange. Scaling is a tricky business, I suppose, but people, because you can do the back of the envelope stuff and just it's like, whoosh, It all works. But, I mean, we'll see an invoking of a fourth dimension. I mean, it's really strange, really strange. But I think that's right, and I think, I think that's sort of an important aspect of why these things need to be separated. And fish are just that's a hard business. Like if you want to get up to whales and stuff, that's hard. Yeah. Sometimes there's data, I think there's been data for whales, but I think it's been made up, basically. That's terrible. Like you'll see a point on a graph and it turns out it's all made up. Okay, so fluctuations. So what we could do is we've got our speckling, right, of points. And so what we can do is remove the best line of best fit and then look at the distribution of the residuals. Right, so we look at the distribution in log space. And if you look at the distribution of residuals, this is for the first, it's not for all of them. It's up to maybe 10 kilograms, I think, in this case. So we're going to divide this is basal metabolism, mass to the 2/3, and then make a histogram out of it. And so we've got this is a frequency, and then the thing that we could do is usually there are a number of nice tests that are non-parametric to compare distributions, and Kolmogorov-Smirnov test, which is not how much vodka you can drink, but it's which is another Russian test. But this is a really a beautiful thing, and so some often called just the KS test. So if you're trying to compare two distributions or a perfect, one you have a theoretical one to a real one, this is one way to do it. And it's not bad. I mean, there's a little bit of a spike in the middle, but certainly from a statistical blah, 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 it's not bad. So you kind of expect that. It's not too bad. That there's a fit, it's going to have some fluctuations. I really want to see a plot with a koala's brain on it. We talked about the koala, right? Yeah, so disappointing. They have tiny brains. And they're smooth. So bad. They really, really are dopey. Okay, so let me just show you this, I suppose. Maybe we can mention it again. So we can do some things like this. Let's say we believe it is 2/3, or we believe it is 3/4, or we believe it is some exponent, any range from 0.6 to 1. We could do that. So a couple of things like that. So this is, using some of these old data sets. This is the full mass range. So this is probably, if we had a 2/3 law, what's the probability that we could get this Kleiber stuff coming out, right, with some fluctuation? So we wouldn't expect it, right? This is a low probability sample, and it's just 13 things, so that's pretty bad. 3/4, yes, this is pretty good, right? Not bad. And again, so it doesn't fit here for this Brody data. This is the livestock stuff. Does not fit for Heusner, which is the meta-analysis of the early 1990s. And 2/3 is totally great for birds. I mean, this is super duper. Not so good. 10 to the -15 is not really. It's always, remarkable. With such large data sets now, you sometimes see 10 to the -100 or something. It's like, that's madness. But if you break it into, and this is for mammals, if you break it into 10 kilogram up below and above 10 kilograms, then you get sort of a different thing appearing. That's the measuring exponents of these. Now we only have five organisms in the Kleiber data set. 2/3 looks tremendous now. 3/4 is not rejecting 7.5. Looks very good. Brody's kind of a mess. The Heusner data really looks like 2/3, right? But not 3/4. So this is this better thing. So what I'm trying to here is Kleiber have just 13 things, tiny samples, and fine regression to the seams. And work just did on this the other day, basically saying it's a mixture of power laws and all sorts of things. Again, not the first people to do it. For greater than 10 kilograms, maybe the exponent, I'm not saying it's 3/4, but it does maybe curve up. That could be an artifact of measuring those larger organisms back in the day. So that sort of holds together. So the probably it's a 3/4, not bad. Heusner doesn't work. It's actually that exponent's too large. So there may be a break in scaling. Breaks in scaling happen all the time. Happens in distribution, the probability of earthquakes of given sizes, and there's a reason. This could be to do with, again, gravity and the way bones start to be structured. So here's the thing. Any exponent you want, we're going to fit the prefactor and then look at the residuals. And if the residuals are, right, so if we've got the wrong exponent, the residuals will be correlated with each other, right? They'll tend to be below and then above the line, or above and then below the line. If it's a really good fit, then they should be just like randomly jumping around from side to side. There are various ways. The Spearman rank correlation, beautiful thing, non-parametric, where you just simply order things, right? So we'll take the X's and the Y's and we'll rank them by size, and now you just have 1 to n and 1 to n shuffled. It's a permutation problem. Primo stuff, really nice. Non-parametric, you don't have to know what the distributions are. So it's the spiffing Spearman rank order correlation coefficient, and you can look that up. It's a beautiful thing. Students, numerical recipes in C. I know this is sort of an old thing. Great explanations. So if you do that, so the game now will vary from 0.6 to 0.8. We'll allow all those exponents, and we're looking at, how do the residuals look in terms of, are they sort of just bouncing around that line of fit, or are they sort of from one side to the other? And so this is for mammals up to just 3 kilograms. It's on a log scale, 10, 32 here, and then all of them in this Huizner data set. And so you see this is the p-value. So you see that it's like really pretty great for 2/3, and absolute, this is 10 to the minus 4.5, no good here, right? So this fit doesn't work. Pretty great again here, pretty great again here, and it's starting to move across, but really 3/4 is not in the game. Wow, there is so much arguing that comes after this paper, and particularly in the 2000s, and I mean we kind of lit a match, I suppose. But this is striking to me, and if you do it for birds, similar kind of thing, right? So there are lots of ways to think about this, but this is a p-value, right? There's a probability that your hypothesis of a 0.6 to 0.8 exponent could produce this sort of this speckling of points, such with presumption that if we've got the right best fit line, then they'll be uncorrelated, right? The residuals will be uncorrelated. I should say the dashed lines are 0.05 and 0.01. I'm sorry, I'm going a little long, but I just want to finish this piece. So class et, and then I've linked this in. I had to add that. These are usually for measuring power law decays, but that's another approach. So anyway, so the upshot is maybe 2/3 works for birds. Mammals, maybe only up to 10 to 30 kilograms. Maybe it's a different scaling regime. There's work from economists. There's a break in scaling in the way limb lengths work, but we'll see. Anyway, if we really do actually have non-isometric growth for shapes of organisms, then we're going to have lower metabolic scaling. That's something we'll get to later on. So pancake cows are not going to work out. Science. Okay. Sorry for going a little long, but it's madness. It's madness. All right. I wanted to show you a little bit more about this unbelievableness. And I know I talked about it, but I just wanted to, I pulled a picture out of the Rayner paper, and I wanted to point to one other paper about this, right? So again, there's this kind of history. This is about regression, which you've learned in various ways. A very simple thing, the ordinary least squares regression. There's a beautiful version of it in linear algebra, which couples with the calculus approach. Oh, I know. I need to be on. Let me find this. Yeah. So let's just quickly refresh very, very quickly. So, and I just want you to sort of know about this, right? So this is the normal regression. So you think the errors are going to be this way, and you fit a line of best fit that minimizes the sum of the errors squared. That's one way to think of it. We use square because we can differentiate that thing, right? Absolute value would be totally fine, right? That would make sense. You want the error to be just the absolute, that's the error. But square is, yeah, works out, yeah. And then variances turn out to be good things and all sorts of stuff, right? So squares are not quite as big a hack as I'm perhaps suggesting. This is if you did regression the other way, right? So this is the errors are all in X and the regression is X on Y. And then there are various other kinds of things where you're trying to minimize something with respect to the line of best fit. But RMA, reduced major axis, or it's standard major axis now, I think, is generally what it's accepted as, is minimizing the area of these triangles. So you're going to have a line of best fit, you mess that around with that, and then you want that line to be such that the sum of these areas, or you could make the rectangles, is as small as possible. And this, surprisingly, is the only scale-independent one, which is really weird, right? And that's the work by Samuelson. So there's a difference, there's a completely separate thread in economics, right? In the 1930s, this guy Samuelson, Nobel laureate, very famous, figures the same story out. And so now we have that tied together. But this is the 80s, 50 years later, completely separate sort of line. And I looked back in Rayner. Rayner doesn't talk about Samuelson at all, right? That's just Anyway, so this is a beautiful thing. And I just sort of wanted to reinforce some pieces about it. The other aspect, so that's how it works again. And then there was this extra piece where you figure out that in fact the slope of this line, we have some cloud of points, the slope of this line is actually the standard deviation of the y points, right? If you just calculate the standard deviation absent the values of the x values, and then the standard deviation of x, so it's basically, what's the sort of rough shape of the rectangle that this cloud of points sort of makes. It's just the ratio of those, so it's very easy. You don't even have to connect the x's and y's, you just take them as separate things. So in fact, which is kind of super weird, and I know I'm just sort of repeating this because it is kind of a weird thing, if you just have an evenly distributed set of points in x and y, line of best fit will be this, but it could be plus or minus, right? There's a plus or minus you always have to figure out. So even if it'll still give us something, right? Okay, but of course the correlation coefficient here is 0. There's no correlation. So one of the upshots here, and I added this to the slides, and this is an example from Rayner. I'm going to point to Labarbera, this paper by Labarbera as well, where he goes and does the same kind of thing. I'm going to mention this in a second. So if you find an old paper or any paper and they've done least squares, so this is a terribly messy looking thing, and you've found that they've done ordinary least squares and reported a slope, so that would be ordinary least squares. Here is this one, right? That's the annotation, the notation in this paper. So this slope is shallow, but if they've reported that, drawn a line through it, but also given you the correlation coefficient, right? They've also reported R, then there's this very nice thing that you can actually just deduce the RMA thing, because the RMA slope is this slope, y on x, divided by the correlation coefficient. So if you have a paper that's filled with slopes and correlation coefficients and they don't know about this standard major axis thing, they've just said, we're just going to do this regression over and over and over. But you know that there are errors in both of these measures, that you really can't treat this as an independent variable, it's measured beautifully, then you can go through and actually systematically correct it. Or figure out what the this slope is for the model where you assume errors in both quantities. So that's a really kind of cool thing. So that's, and just there are some calculations here, right? So the slope, so here's the correlation coefficient in here, it's 0.35. So you can see, there are two things here, right? We're going to multiply, so 1 over r squared, this is a pretty big r squared and 1 over r squared. That's the difference between the regression of y on x and x on y, right? Those two slopes, they kind of give you the bounds of the slopes that are possible. Like if for some reason you think this is the dependent variable or this is this one, this is how variable things could be. And that's a pretty big range in this case. It's a factor of 5 or a factor of 0.2 closely, roughly. So if you just had correlation coefficient is here, it's the 0.43. You knew, I think it's here. Here's say this correlation, 0.334. You'd divide it by the correlation coefficient, and that would give you the RMA one. And then you could divide it again, and that would give you the slope for the x on y thing. So that's sort of helped sort of salvage a lot of papers that are floating around that just sort of, where people have just sort of used this standard least squares thing when they shouldn't have. Which is pretty good. Okay, yeah. Yeah, so that's all in there. And I've sort of just written this, right? So the upshot is that if you just have ordinary least squares and you have the correlation coefficient R, then we can figure it out. So that's good. La Barbera, he goes through and sort of points to a lot of papers, digs out their data and says, fix these things up. From what I understand, and West, who I've been talking about a little bit, and I'll remind you, he'll come back again, Jeff West, actually told me that I think this guy resigned from the Science Magazine Board of Editors over West paper. We're going to get to West paper in a little bit. This is a paper that had, I believe, 9 reviewers, super controversial, including someone who said, that's it. You publish this, I'm gone. So, yeah, interesting. Okay, so we looked at the madness of these things. All right, that's a little tool for you guys, right? It's something to think about. Yeah, okay. Okay. This was this observation that if we do so all of that's sort of an aside, because when it comes to measuring, say, metabolism and mass is something we measure well. So we're going to be happy with that being so in fact, there's a pretty good argument for using ordinary least squares for that kind of thing. Mass, you put your thing on a scale, your weasel or your elephant or whatever, and you can measure that well, but measuring metabolism, that's a messy thing. And depending on the range over which we do our regression, then, really does seem to conform to 2/3. And I'd sort of given this story that we started in the 1850s with humans making decisions about how to feed humans. It was not very good. The tobacco plantation in France with a 2/3 scaling for energy, rate of energy use, basal metabolism as a function of mass, so 2/3 power. There was the dog story in the 1880s from, and then we ended up starting to kind of creep up with some of these regressions. We could see what was going on, I suppose. It seems maybe larger mammals have a different thing going on. Maybe they're just harder to measure. But certainly for birds, it looks like 2/3. There's a lot of 2/3ness there. So what happened? What happened? I guess I've gone through that. It just became calcified in people's heads. Of course, we saw a vote. They voted. It's nuts. It's really strange. So I went through this. Okay. This is all good. Okay, good. And let's say here. Okay. So there was this last statement, I suppose, which is that the exponent 2/3 seems to work very well for animals, for mammals up to about 30 kilograms. That's a ton of mammals, obviously. Birds, certainly the full range that we have. Maybe there's a different scaling that's happening. This is not really sorted out, but we'll sort of dig into that a little bit. That's just, gravity starts to really play such a role that you really don't, your weasel isn't just a bigger mouse sort of thing by isometric scaling. It just really starts to be a little bit different, right? That's a mechanical problem. You got to hold yourself up. Okay. So there have been a lot of papers, especially since the 2000s, but there have been many, many papers for 50, 60 years around this, people arguing about whether it's 3/4, 2/3. This is a 2005 one. They sort of discard. They say the large herbivores are no good, which is weird. Then there's this one by Glazier. It's not universal, and they say there really isn't a scaling. It's like a big measure, I'm trying to say mess, I suppose. People keep coming back to that it's like a couple of scaling laws together. There's a paper just published on that. Beyond the 3/4 power law, right? So this was an old issue, intra versus interspecific. People really thought that intra within species would be a 2/3 scaling. Obviously, they don't vary much across. There's not a lot of size variation within a species, so it's hard to get any scaling at all. And then 3/4 across species. So this was sort of this beautiful story. So finite size scale. So this is just a disaster, right? Really is a disaster. I'll come back to some more papers in a little bit, but that was just one slide of people getting very confused. It's unbelievable. Okay, all right, so there is this connection, of course, another big branching network story that we've talked about, probably too much, is river networks. And so this has been floating around. You've seen this picture before, but the idea is that we can go out to some basin, and it's going to have basins within basins, and there'll be some typical mainstream length, some area that it drains, and there's some scaling to that, right? So the question is, does this basin look like this one if we scale it up isometrically, or do we have to stretch it in some funny way? So Hack's claim, and so the 3/4 thing is interesting because it's not what you would obviously expect from the 2/3 thing, so it means there's some magical thing happening. This will take a physicist to figure out, kind of idea. I'm being obnoxious. And then, so this is just this old study, and it's not satellite data, it's pretty messy, it's back in the 50s, that's fine. But you found an exponent that was a little bit higher than a half. So that's an anomalous or allometric scaling. We'd expect a half, right? This is length and area. So there have been other studies since then, and we've gotten between a half and 0.6. You see this, another quest for universality, right? Is there some magical thing that's happening? Okay, a lot of these studies are on small scales, and this paper appeared in 92, it's Montgomery and Dietrich. This was in Science. Bill Dietrich, very famous geomorphologist at Berkeley. And this was putting together, obviously, a lot of data here. We're going from areas of 100 square meters up to 10 to the 13. So this is a good bit of scaling range stuff here, right? So we've got 11 orders of magnitude there. Obviously, you get more for area anyway. It grows much faster. So length is going from, we've got 6 orders of magnitude there. So the regression on this thing is 0.49. So the exponent it's looking pretty solid for a half, right? So that was a bit of a downer for the whole, it's amazing and special, right? Okay, so that was a bit, so why is, what's going on with this? This is, actually this is from a paper we did, it sort of conforms to the Dietrich thing, which was really a mess of everything, right? They put all sorts of stuff in there. This is just we're taking the biggest basins, and we're just taking the actual whole basin itself, right? And not any internal ones. So that's not a bad thing to do. We're comparing, of course, across continents, and that's looking good for a half. So another one of these things where the obvious thing or the simple scaling thing seems to work. There's a reasonable, there's not a lot of data here, so there's a reasonable standard deviation. This is, I think, is it the Mackenzie River in Canada? It's the Mac something, the Muck. It's, geology starts to really matter, right? You've got mountain ranges and things and can constrain what's possible. So this is a really, right, large area, relatively small length, so it's sort of something that drains in a quick way like that. Anyway, that's fine. Okay, so. So now we're going to talk about theories for all of these things, and this is going to be an interestingly complicated history as well. So we've mainly gone through data, a little bit now for river networks, but it's mainly been about data, I think, is what I've shown you. Okay, and we've tied ourselves in knots. But generally speaking, on the theory side, people, by this point, have decided when it comes to biology, it's a 3/4 law thing. It's just there. So now the game is to prove it with a theory, right? So that's right. It's game over. Right? So now we've got to come up with a beautiful story for it, and it's there, and you'll win fame and acclaim, right? So McMahon, who was a mentor to Strogatz, if some of you will know his name, that I've mentioned him quite a bit. Watson Strogatz, of course, for small world networks, but Steve Strogatz has done a lot of cool things, especially around synchronization. Anyway, so that's a connection there. So he was at Harvard, I think, talked about elastic similarity. So this is really allometry. And he was, by this point, he's like, well, where's this 3/4 thing? So his claim is that it's to do with the shape scaling of shapes of organisms scaling with quarter powers. This is bad. He does cite this Hemmingsen, and this is the crazy Danish booklets that are just bananas. that have like slime mold and stuff in them, things made up. Right? This is the one that essentially assumes 3/4 to be true and is just really fitting the y-intercept. So this appears, there does seem to be evidence for this kind of scaling for ungulate legs, right? That they do have allometric scaling. They aren't just simple isometrically scaled up things. That's one. So it's just sort of a very rough statement. You know, he doesn't have some beautiful story for everything. And we'll get to this later, but the shape and how metabolism should work is never really connected. And so let me see if I can say, we'll come back to it, but just give you the idea that if we have, say, a collection of spherical cows, right? So they're scaling up, and we imagine they're, you imagine just normal cows scaling isometrically, but spherical cows are funny. So they're growing in size. And then you have pancake cows, right? They're pancakes with legs, and they're scaling, but they're not getting thicker, right? They're getting thicker very, very slowly, right? Then the surface area ratio to volume is much higher in those pancake ones, right? So they give off heat much faster. It's a sort of a bad situation, right? So you would think that's problematic. You would need it wouldn't be a great sort of system to run. And then you also have to think about how the network inside that thing works. And we'll get to that later. That's a bit more complicated. Because it's not just the surface area. You do have this network from a single supply, the heart, somehow supplying that thing. So we have to think about how that scales. And it turns out, spoiler, because science, what we'll find is that it only matches up for isometric scaling, that the network structure makes sense with the heat given off story, right, with the surface area. Right? So if they're mismatched, if you have an allometrically growing shapes, then the network can't match up. The way the network will scale can't match up with how the surface area scales. We'll come back to it, but I want you to have that idea. And that, I think, is a really beautiful thing. Yes. Okay, so here's the sort of thing. This is a science paper. And just messing around. So someone's been measuring chest circumferences of monkeys and things like that. And he's playing around with trees, right? Trees have a slightly different story going on potentially. Do they though? I don't know. So this 0.63 here would be sort of like, this is 5/8 maybe. Anyway, sort of just points to a little bit. If you can dig into it some more if you want. Okay. This is interesting. This is actually Hemmingson again. So has a suggestion here perhaps that there's a 2/3 power, right? Possibly a 10K thing. There it is, 0.69. Oh God, such a mess. And you can see that departure in that graph up there for larger things. And this is for surface area. Yeah. I have a memory that there was some effort to measure the surface area of cows by painting them, and how many clicks of the roller it took. It's kind of tricky. I mean, you could, unanimal the animal and you have a skin to measure, but that's it's also not, that might not work out either. What's that? Yeah, so he's right, gets a little, that's not ideal. Yeah. Hemmingson. Yeah, so that's interesting. This was actually a surface area plot. And he, tons of citations here, right? There's horses and wow, a ringed snake. That seems tricky. Yeah. Although maybe easier to measure, right? You just measure the length and then multiply by put a little tape measure around the snake. Can you imagine? People with tape measures and snake, it's just like a disaster, right? Some of these will be easier than others. But see those names, Benedict, Brody, Hemmingson. I hope he did this well. I don't think so. Frogs were in there, fair enough. Yep. How much does it take to paint a frog? Unbelievable. But an interesting, tricky thing. And then they have sort of folds and so on, and then when you think, so that's a problem. Okay. Pratchett's surface area is larger than it should be, obviously. I try not to put this in photos, but he kind of has an udder. He has a little pink belly, and he kind of has, so he's a bit of a moo cat. Yeah. Yeah. I know, we're trying to lose weight for it. Anyway, it's not working out. What was that?
Did you ever tell him?
We have just polite conversations. It's all right. It's usually about the humans involved, about how much we've fed him. There are strict rules on the wall now, and like, do not fill past here. But he's very cunning. Okay. Yes. What was I thinking about the other day? There was some... Okay, so there's a game called Nakatomi. Does anyone know there's a game where you basically, it's a Japanese game, it's like a nice little 3D thing, and you have to buy treats and cat things and put them in your backyard? Okay. Interesting game, right? So it turns out my oldest one, the 15-hour sleeper one, we looked after a neighbor's cat for a while, became very attached, and then had to go back. And then she played that game until we eventually adopted Pratchett, which was basically her going to the Humane Society over and over again for therapy. And then eventually, we adopt this cat. But it does lead to the suspicion that cats made that game, right? In their efforts to harness humans, which clearly is why the internet was invented, they've gone one step further with the video games. It's very clever. Totally worked in our case. Yeah. Okay. All right. Let's look at some madness then. I think we've looked at some madness, but this is really strange. This is a 1977 Journal of Theoretical Biology paper. It's about three pages. It just flat out says, well, what if biology is somehow four-dimensional, right? There's some sort of extra foldy bit in there, maybe fractal. I'm not sure if this person even says fractal, that we're not really figuring out. Because if it's going to be this 3/4 thing, this is the simple observation. If surface area scales as mass to the 2/3 in 3D, but it scales as mass to the 3/4 in 4D, right? So and they're sort of touching on something that's possibly maybe works out, right? Because say our lungs basically fill space. So there is this feature of biology that's trying to we have fractal structures in us. Obviously, the branching networks we've talked about, but say the lungs. I don't know if it's really true, but it's like tennis court, right? Was sort of always the rough idea of how much area that we have in here if you put out the alveoli in a very bizarre and Hannibal Lecter-like experiment. Anyway, so sorry. See that ad? That's not good. We shouldn't be in that thinking space. Okay, so fair enough. Yes, sort of maybe it's not really a fourth dimension like the Twilight Zone or something, but it's like there's some scaling, and we'll see a ridiculous thing again a bit later on. But this was pretty nuts. It just sort of says 4 dimensions would work, right? Because then it would be 4 minus 1 over 4. Yeah.
This really is a church.
Yeah, this is pretty silly. Yeah, some strange people. Well, you make up stories. If you're a monk and you're really into it, you can make it happen. Yeah.
Is that like a real thing? Like what if we talk about like one organism over 9?
Yeah, so that's a I don't think that happened in here. Let's open the tome of Bloom. It would be great if it was related to the Arrested Development Blooms, but I don't think so. Okay, so may have committed some light treason. Schmidt-Nielsen, which I haven't talked about that. So here's the scaling. Says it's a value close to it, right? Here are all the things. Rubner with the dogs measuring the things. Here's McMahon, as we've talked about. Let's see. See, it's really short, actually. It's just these things. Put a pi in there. Very nice. Bull barking, right? So he's citing some math. Wow. And then said, this is just really unnecessary. This is the volume of a sphere, right? With gamma functions, the full business. You don't, a little bit overkill for what we're doing, right? It's just an envelope situation, people. Look, it's just, this is fantastic. And then says, then here's our scaling, right? This is all a bit too much, but basically it should be just volume, or area scales as volume to this, and this is n minus 1 over n. Also, I mean, just from a taste point of view, n is not for dimension. It's a number thing. Like, this is just hurtful. Okay. It is funny. There are real tastes and cultures in the way people annotate things. Like, computer scientists just don't care. You know, they're just going to have a variable and it'll have a name and maybe an underscore. Fine. To the power of 5. You know, they'll just do it. And you can read it. It's like connected to the things. And that's fine. Pure math gets very, you know, they're into Cyrillic or whatever. It just like goes right under Gothic things. You know, fine. That's also cool. There's some beautiful alphabets that we have not really used, which I think would be fun. I mean, Greek obviously is a great place to go. Oh, yeah. I need to get that one out. There's a nice little network which is, you know, in English people typically say it's all Greek to me. There's a nice little network of what languages say which language is their Greek. And for a lot of them it's Greek, a lot of them it's Chinese. But I think for the German it's Spanish. Anyway, so it's kind of fun. It's all Spanish to me. Anyway, so they're just saying it. I'm just saying it. I'm just saying this is possible. Maybe the physicists don't really understand. You know, they've been talking about 10 dimensions by this point, and 29, was it, for string theory? And then they went to 10, and they're all rolled up tight, right? So maybe one of them is rolled up tight. That's where Pratchett's got an extra one. So it doesn't really go much further than this. It's like, just here. I haven't looked at this for.
Exceedingly simple derivation of the exponent A equation 1 by some underlying simplicity in nature. The latter side.
So there you go. But you're right. We're gonna make length out of other ways. Yes. And so let's see if it says time. Okay. Ratios of quantities determine mechanical stability. It's like, okay, we're just like fussing around in the drawer to find another thing that looks lengthy. Yeah, wow. Energy, yeah. So, maybe. It's pretty funny, right? But that's just been sitting around and, oh dear. Looks good. You can throw in a gamma function. It gave it a bit more, panache. Right, okay. Obviously a bit silly. I think that's, we should go with that. All right. So we've got Reshevsky, who's very famous for a while as being this part of sort of cybernetics world, I think, but was one of these physicists who were going to explain all of biology, and it's going to be like we're going to be able to control it, and it's our stuff. So he's fallen away, but he was at Chicago. But here's this thing, and I've struggled to find this again, but it's a paper that just sort of basically says, but this is using networks. Mentions networks, thinks about, okay, this is the big transition. This is a bit of a lost paper, but the idea was, Reshevsky had to say, you've got a heart, you've got this, let's just make it a hierarchical thing, it's got to supply energy, so what does that mean for our organism? I've got to find that paper. It's very lost. And that's all I've got for a citation there. So, now we come to something, and this is a beautiful, beautiful idea. This remains a beautiful idea. It's wrong. The paper is a disaster, but it's got 3,500 citations. It's quite famous. But it is wrong. But the basic story is clearly right? Which is that we have networks inside us. Most things, so insects don't. They sort of do, but it's not being pumped through like us. They're just sort of, it's more of a diffusion story from what I understand. They have some channels. There are some networky structures even within cells, a little bit, but there's a lot of diffusion there. But certainly for mammals, birds, fish, networks, right? Blood networks. What else should I put in there? Yeah, platypuses. Okay. And so this is a sketch. This is a mind-bendingly frustrating paper. It appeared in Science in 1997. As I said, 9 reviewers, which is not, that suggests Science wanted to publish it. Because this is what you do, right? And we've talked about this with contagion spreading. someone says it's good, and then maybe you stop because you're like, yes, like I've got my thing. Or if you really want it, bad, and then this person says it's good, it's like, okay, there's one, right? So, a little bit weird. Usually that's done well, I suppose, although peer review should be burned to the ground. So this is a mammal. This is what they put in for a plant. This is clearly also not right, but and they don't really model a plant flow. Plant fans in here, right? This is not good. Yeah. So xylem, right? You have cell structures. I mean, it's quite an interesting thing, but these are all little broken up cells and stuff moves through it. But it isn't a clear path. I mean, functionally, you could sort of say it's sort of, if you look at how things flow, it sort of looks like this. But in terms of, you want to say there's a tube and it has you can't do that. And they don't really do that in this paper, but they just sort of say, oh, it's true for plants as well. They use a purely hierarchical model, which is fine, right? I mean, we know it's this Tokunaga branching structure that's more complicated, but this is basically okay. And we're going to have a series of tubes, right? We have a series of tubes like the internet, and this is going to be, the velocity will be their u's. If I sort of, how much I carry this, I'm not sure I should talk about it too much, but this will be their velocity. There's a radius for a tube and a length, and then there'll be splitting, and there'll be some drop in pressure. Okay. We've already talked about Poiseuille flow. That was for the optimal branching story, and that gave us Murray's law, which is a very beautiful thing, right? The cube law, and that really does hold up. Just to say again, that held up nicely for trees. The more the xylem was just for transporting stuff, and less about actual structural integrity. But we have it as well. Murray's law applies for us in the outer parts of our blood networks. And the connection there is that, or sort of the good story there for us is that also means things slow down. Because blood has to, it's going quite fast here, and it has to actually sort of slow down as it goes through the capillaries to exchange the goodies and get the bad things back. Not a biologist. But I believe they are exactly the terms they use. Okay, so, all right. But here's a big point, right? They say, what does it mean? We've got these things, these organisms running around, they've got these networks, they have a central source of energy, they have to get the stuff out. If we think about the networks, what will that say? How will that constrain their energy usage? And again, this is about their basal metabolic rate. So you kind of have to think about it. It's not as fast as they can go. And of course, we have that's sorted out by having locally stored energy that we can explode with, right? That we burn up within less than 10 seconds for humans. Right, it's crazy how much we talked about this in scaling, right? I mean, it's the 400 to the 800 in running is just a huge change, massive change. You go from monsters with giant quads and things to people who are long-distance runners, basically, at 800. Yeah. And there's a little bit of strategy. You can kind of lurk around at the back. But 400, you're just like, because you're just burning off everything you have. And you can't really do that at the next thing. Anyway, this is about resting. This is a resting energy. This is just stuff like you're just sitting there, you're just running it. Yeah. Okay, so profound idea. And this is what they assumed. Hierarchical network, which is fair, fine, right? There's been some efforts after that to fix it up. So some important pieces. So the capillaries are invariant across organism size. So they're going to really, in this paper, if you go to it, they're going to frame it around mammals. And so the capillaries in an elephant are the same as those in a mouse is going to be the idea. There's some papers that sort of look at that too, as to how true that is and so on. But it seems to be roughly true. I mean, we've got this evolution's working away, busily making weird, strange organisms, but it's constrained by what's come before. So it does seem that, maybe, so I wonder what this is now. But, a cell from an animal of different sizes, it's a mammalian cell. It's not immediately obvious that it's from a bigger or smaller thing. But I think the mitochondria might give it away. So then there's this beautiful idea that you would make networks. It's fair enough that, and evolution doesn't always produce optimal things everywhere, but it produces a lot of pretty good things, right? Platypus is a weird one. But did you want that impedance to be minimized, right? So that sort of sets us, if we can, now there's potential to construct a model where we could, roll out some minimization technique and try and find some constraints on what sorts of networks work. So the upshot was that they got the basal metabolism scales mass to the 3/4, networks of fractals. So this was an interesting result, right? Fractals have been talked about for a long time. We have Mandelbrot, Benoit B. Mandelbrot, and the joke is B stands for Benoit B. Mandelbrot. But so he made up, he comes up with this term. As we sort of looked at here, Horton was the first one to apparently come up with a quantification of scaling like this for recursive structures. And mathematicians kind of love them, but there haven't been many generative mechanisms. Obviously, nature makes these things over and over, but there haven't been a lot of truly generative mechanisms. There are fun little math ones to make a Mandelbrot set and so on. But that was in itself a kind of a cool result. Quarter powers are everywhere, so I am going to open up the West. This is such a wow. And look, I got along well with West. We worked together a little bit on trying to transfer some of this. So, you know what? I'm going to see if I have. Interesting. This will be scanned versions where I've annotated it. Yeah. This took a lot of messing around trying to figure out what was going on with this. I think that's a second effort to write on it. Is it? Yeah, that's another one. Yeah. God damn it. Wow. Okay, well, let's look at the messy one. That's fun. I don't know what I'm doing over there. Okay, all right, so Darcy Thompson reference. Okay, so West, Brown, and Enquist. So Brown and Enquist are ecologists. They start off, they say, blah, blah, blah. Model assumes energy dissipation. That's the big deal. Terminal tubes do not vary. And, big statement. General model for the origin of allometric scaling laws, right? At this point, is an absolute mystery, right? 977, we have, maybe there's a fourth dimension, and everyone's like, and, no one has a story. Here's the model I just showed you. And I think this will be useful to look at. So they don't derive this, but there's sort of all these scaling relations that one could talk about. So this is useful. I mean, the predictions, of course, will all make sense. But they claim to get all of these things, right? So there's aorta radius. They're going to say that's a 3/8 power of mass. So this cross-sectional area is a 3/4 power, 2 times 3/8. And so the idea is that the blood you're pumping connects with how many capillaries you have, and that should be, what do they call it? Number of capillaries, here it is, 3/4 power, right? So it's actually in our structure, right? The number of terminal units for which the energy is exchanged out of is scaling this way. And if you think about that, that's not, so this is mass to the 3/4, it's scaling less than mass to the 1, so it means that each capillary is trying to service a bigger and bigger area. Right, so the volume, because this number times the volume that a capillary services has to scale as mass to the 1, right? So if this is only scaling as mass to the 3/4, then the service volume is scaling as mass to the 1/4, and so as you go up through organisms, you get to an elephant, this capillary here is serving more and more tissue. But the cells are still the same size, right? They're not changing. So that's taking longer to diffuse from a capillary to get out to that mass. If that's true, right? I mean, if that's true, this is a tricky business. But there are some very, smaller pieces. I think there's a lung one. So lung volume scales as mass to the 1. But then there's some very, like this one, area of lung is scaling as mass to the 11/12. So it's all based on quarters. But this is the thing, like we do, right? This is an area, right? This is an area which Dimensional analysis would give you a 2/3 scaling, right? That's as a function of volume or mass. This is getting pretty close to, and we know that. I mean, we know that lung volume is lung area is like this tennis court thing I was talking about. Must scale in a way that's pretty high, pretty close to 1, because it does fill space. All right, so anyway, there's a ton of things in here. So it really kind of hinges on them getting this, the number of capillaries. So you can imagine you make this network, it ends in all these points, and you imagine another network that brings it all back, right? So there's the arterial flow and then the venal flow. But if these guys, if that scales as mass to 3/4, then that tells you that the metabolism scales in that way, right? You've got a heart, you've got some number of units out here, and they're the things that really, they're the little motor bits, right? Yeah. That's the idea. So that's it's sort of a beautiful story. What's kind of weird in here is, this paper is, the defense was that it was a much longer paper and they had to cut it down. This is always true of science, right? Science is like, "Ugh." It's still a long paper for science, it's 4 pages. But what happens is you get this calculation, which is also somewhat wrong, but not bad, where they assume Poiseuille flow. So again, Poiseuille flow is like smooth fluid flow through a tube, and that was something where, and I'll have it here, the impedance of the tube is proportional to its length divided by its radius to the 4th. So radius really, affects it. And that's smooth flow. We don't necessarily have smooth flow from near the heart, so that they have to make a correction. But for Poiseuille flow, which is sort of out here, they get Murray's law. But they get that the metabolism scales as mass to the 1, right? They don't get 2/3 or 3, they get mass to the 1. So they're like, okay, this is an illustrative calculation because it shows how to do the minimization and so on. And they say, for a more complicated thing and with a different impedance, we get the 3/4 thing. It is hard to work through this, and it was very clear after many months that no one had really done this, including the authors. So, it's still something that's argued about because it's full of math and it says a thing, and wow. But it's sort of, I think it was just like they messed it up, but then they stuck to it. And you see people have kind of gone and worked with them and then fallen away from this group. It's messy business, like they've been true believers and then they've fallen away. So this is what I was saying, right? So Poiseuille flow, that if you use this impedance, and so let's look at what this impedance is. This is the impedance for a little vessel, right? For a little tube. And what we're adding up here is, okay, so what's happened is, this is a series impedance. Let me do it. This is good. Yeah, good. Okay, so we're gonna have our ticker, right? A little green P, as Australians will say to people who aren't tough enough. Okay, so we have an aorta and branches, and they're just going to say there's going to be some branching ratio. And they use some funny notations, but basically there's a branching ratio that's consistent. So if it's 3, right? If it's 3 here, say, then it'll be 3 again here, right? Fine. And then there's some ratio of, so there's going to be, at each stage, this is k equals 1, k equals 2. There's going to be a radii 1, radii 2, right? So that's the radius of this thing. Okay, that's fine. Right, radii here. And then there's length as well. So you've got to have a length. And then there's going to be the velocity. They'll call it something like this, u1, this should be 2s, etc. And just like Horton's, what's the ratio? What's the ratio here? Ratio of change from order to order. So it's like Horton's laws, right? Basically adjacent to that, the same story. All right. So, impedance, right? So if we have resistors, if we have Z1, Z2, Z3, so this is series resistance. Series works in the same way. There's this beautiful kind of duality between hydraulic and electrical systems, network systems. So this is just the overall impedance you just add, right? You just add it up. And then parallel impedance. So let's say we come in here and then we have a resistance here. This is a toaster and another toaster. I was trying to make a Pratchett joke, but I can't do it. And then, so what's the impedance for this whole thing? Do we know? What is it? Yeah, right. It's an inverse thing. So 1 over Z1, and you can figure this out from first principles. So now, if all of these Z's are the same, or if Z1 equals Z2, then 1 over Z equals 2 over Z2. Z1, I guess I should put Z1. Right? So if this, then this. Right? So if we have a whole bunch of them, if we have n of these and they're all Z, is this messy enough that am I making it bad enough? If we have this situation, so we n of these, then the Z overall would actually be just Z divided by n, right? Which makes it's easy to get through, right? So if you're trying to push stuff through here, you've got all these impedances, but it's easier because there are more ways to go through it, just to sort of have some sense of it. Series, of course, you're stacking things up, makes it harder to get through, so you just add them. So the two versions are really, if you have n of these in a row, it's just n times z, and if you have z in parallel, you have n in parallel, it's going to be, you divide it by n. All right, so let's kind of complete that one. So n in a row, then z overall is equal to, that's some attempt, should not write prescriptions for people, equals n times z. How do we feel about that? Mm-hmm. It's a good thing. Whoop. Okay, so that's really what's behind this top formula. You've got one aorta, it splits, keeps splitting. This is the number of tubes at the kth level, right? So it's all split out into k of them, and they're all in parallel, so we're going to divide by the total number of them. But then we have all of these things in series, so the sum is, as we move out, I'm using the notation for the paper, which is horrible, because there's an n here and an n here. This is the number of levels to the hierarchy, and that's the number of, it's really awful. Okay, so lengths at least look like lengths, and radii look like radii. They kept pi, that was good. Okay, so this is, so does that make sense? So this is making it easier to get through because they're in parallel, but they're all in series, so you have to push it through this network. So this is a very pure network, right? It's a pure branching. The impedances are exactly the same as you go through it, so you can write it down. If there's some sort of variation, it becomes much more complicated. And if you try to do the Tokunaga thing, again, more complicated because you have to get all these little side ones. Okay, so the upshot is, and I'm not going to put the calculation right in front of you, basically, and I just have it here, the Poisson flow, if you assume that the whole network has a smooth flow, you get basal metabolism, as I said, scales as mass to the 1. It's a Lagrange multiplier situation, and maybe we should include it. You know, you've done Lagrange multipliers in fun ways. You know what? Yes. It's very opaque. It's not done in the paper. There's no supplementary material. So you have to you just have to, it's like they set it up and you have to go and figure it out. This is going to be the function we're minimizing. And then we're going to have things like the sum of all of the tubes is proportional to the volume of the organism, for example. Like maybe you want that, right? So that's the blood. Like the total blood in the thing is proportional to the organism. That turns out to be, so it's a reasonable assumption, right? Not everyone gets there, but that is a true fact of things, because some people have taken their organisms and squeezed the bits out of them and measured the blood. And it makes sense, right? You can't have allometric scaling for blood volume, because, as I think I said, right, at some point you're going to have an organism which is all blood, which is not so great. Okay. So it has a few constraints, and I'll put those in on assignment. There's going to be that. There's going to be some constraints about, there's some weird ones, like the length cubed. I think they want that one to be constrained in a certain way, and that's supposed to be space fillingness. Ugh. But if you put those things in, you differentiate it, everything kind of works nicely. You actually get a consistent answer, but you get this. So this is right? This is actually what's presented in the paper. You get this result, and it's like, oh. Well, in fact, there's a logarithmic correction, but fine. Mass the one. So then the paper turns in the second half and says, well, actually, these networks are weird, right? They're a little stretchy. So we have to wheel out some more advanced fluid mechanics. I mean, this is a very super cool thing for impedance. There's work by Womersley, I think it's in the 60s, that basically came up with this impedance for an elastic tube, right? So we've got tubes with pulsatile flow pumping through these things, so they're going to go whoop, 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 right? Yeah. I think that's a reasonable, yeah. Again, biology. But you've got a tube that's going to swell, right? So stuff's going to go through it, and then it's going to have a weird impedance. No longer does length length isn't in this impedance. This is a very strange impedance, right? So this tube could be 10 times as long, and the impedance that you see trying to force the stuff into it doesn't change. If you increase the radii of it, then the impedance goes down, right? But not as fast as it did for, right? This is 2.54, so not as fast. And now the wall thickness matters. That's what this is. This is the thickness of the tube's wall, right? So if that's thicker, then it's going to be a stiffer thing, I suppose, is sort of what's really being encoded there. So if it gets thicker, it's going to not be as easy to push through. Anyway, it's there. Their strange scalings are 1/2 and 5/2. Okay, so same idea. We're going to put our constraints out here and minimize it, Lagrange multipliers. So what happens is you do not get a consistent set. Mathematically, it doesn't work. It just doesn't work. Right? That's a terrible thing. We're going to do it. But the thing is, you do not get a consistent set of results. You get some things about the radii and the lengths maybe and so on. They have some other things, and now you have to think about what happens to these, how these scale as you go from the aorta down to the smaller things, the widths, the tube wall diameters, not diameters. The thickness of the walls, that's what I'm trying to say. So you have to think about those things scaling, so it's a new kind of Horton law for that one. So let me summarize by saying it just explodes into flames. It goes thump. It does not hold together. It just does not hold together. Now, you could abandon the Lagrange multiplier thing, and that's sort of the defense. They're like, okay. If for some reason you ever see Wes talk about this, he will pull out slides, like, I don't know, he must do something now, but for a long time he pulled out the old school slides, just says it kind of works. He knows, we've talked to him, he knows it doesn't work. He knows, right? Yeah. But it's whatever. Okay, so the model really doesn't give you this massless 3/4. It doesn't give you that networks are fractal. What you really need, actually, it's not this fractal, but as you go from level to level, this is the thing, and this is true of impedance in general, is that whatever the impedance you sort of see at this level, you have to see the same one at the next level. And it's called impedance matching in electrical engineering. You want to have things be as match up exactly if you can. It has that, so you could have, a big branching ratio and then a smaller one and then a bigger one, as long as the radii and the lengths change such that basically collectively the impedance of all those tubes put together looks the same, right? So it's like having a whole bunch of like tiny straws that you try, I don't know why I'm saying that, but tiny straws you're trying to drink out of, and then one big straw. It's fine as long as the lengths change in such a way that, it feels the same, and you're wondering why you're drinking with straws. Okay, sorry. But you have one big straw and then lots of little straws, and then, right? And it doesn't really matter. The branching ratio doesn't have to change. It have to be the same as you go all the way through. It's just that the branching ratio and the change in the radii and the change in the lengths have to collectively combine so that it makes it look like it's just one big tube. Whatever the impedance of that first tube is, the aorta. They definitely get the Murray's law for the outside, which is nice, but we've already done that. But they sort of got it in a networky kind of way, but we've already got it. And that's what I'm trying to say here. This impedance is distributed evenly. Yeah, that is really delicious. We're going to get back to this Ronaldo guy that played rugby for Italy, but we really worked on this in like 98, 99, trying to make sense of it. It was a huge story at the time. We eventually published a paper, which an incredibly painful thing to do. This is a real problem with science. I mean, we like West, right? But we had to write a paper that we called it Re-examining the Three-Quarter Law of Biology. We put in quotes, I guess, three-quarter law, sort of like that. But we went through all the data, and then we went through the theories and showed nothing worked, and also the data more strongly showed you that it was really 2/3. But it's really painful to do that, actually, and this is an unfortunate thing with science, because you sort of say, it's kind of wrong. It was beautiful, but it was wrong. Sort of weirdly, no one else in the world was sort of thinking about this. I mean, I was running around with the branching network stuff. I mean, people loved it. It's a big story, but no one was really thinking about it. I ended up being the person who was quoted as saying something a bit different, like in Nature and Science when it was talked about. I kind of had little quotes in there saying, something like it's a beautiful theory, but it's wrong. Some random graduate student. It was a bit of a weird situation. So not ideal. Anyway, so we can still do things. We can say, okay, it's distributed evenly. We can assume the networks are fractal. And then you can get to this. And I'll sort of have to finish a little bit. But here's the idea. You possibly could get to this, which is this. These are sort of, and I'm using notation that I've tried to implant on top. So these are Horton-like ratios for the numbers of vessels and their lengths and their radii as you go down. And this is because, so with the Horton stream ordering stuff, we started with the small ones and went back up. So here we're starting at the heart and going down. So they can be framed in this way, right? So the number of vessels increases as we go away from the aorta. This is going to be up the other way, unfortunately. This is wrong, and this is wrong. So these are going to be smaller than 1 and smaller than 1, because they're getting smaller. So it's the opposite to the Horton stream ordering thing. That's terrible. There's so much that's done in getting notation sorted out across things, right? Because you actually figure out things are really the same, right? Yeah. RN, RL. I'll see if I want to fix that up. Okay, so if you go through all that, this is this big thing. So we're going to figure out, here's the claim of the upshot, is that the number of capillaries is going to be proportional to the basal metabolism, and that scales as mass to an alpha, which has these parameters in it. It should sort of seem reasonable that these ratios will appear, but they appear in this very special way. And right, it's a ratio of these two logs. And then we're just going to assert these things. This is not going to come out of any calculation, but this is going to be area preservingness, which means that the area of a tube, and then it branches into some smaller tubes. The cross-sectional area of those tubes adds up to the cross-sectional area of the parent tube. Sort of okay, right? So we're just going to say that. And then space fillingness, which is a little bit funny, but the idea is that, this is a bit weird, that all of the tubes of a certain rank or a certain level, if you add up all of their volumes and you add up all the other volumes, that they will fill space. I'm not saying this, but I'm just, these are things they get to. You could just sort of claim them straight up. And if you do that and you put these things in here, you've got a minus a half and a minus 3/3. So if you put those pieces in here, right, you're going to replace RR, this ratio, with Rn to the minus a half. You put it here. So that will be Rn to the minus 1. You put the RL one in here. That would be Rn to the minus 1/3. So there'd be a minus 4/3 here. Log of Rn, log of Rn, they cancel. That minus 4/3 comes out. It's on the bottom, plus 3/4. Magic. Yes, so that is quite, it feels fantastic. And I've showed this is probably not a bad place to stop. Okay, good. I've showed this slide before, but I couldn't explain quite what was up here. They don't have a prediction for what those ratios should be, but rather just combinations of them, right? That's fine. So we can't really say what the theory would want here. These ratios, are really not super consistent across organisms, maybe a little bit, but they seem to be, within organisms, they seem to be somewhat similar, right? I mean, look at this, it's 1.5. These are different humans, and this, these are different parts of the same, one of our porcine friends, and very similar scalings. But you can see there's variation across here. And if you construct these different kinds of combinations, and this alpha, which is made out of all three of them, this is what they predict, and you get quite a range, right? So the pig, if we use their theory, and actually looked at data which it's not too. So very few people. This is not even published. And I was telling my friend, I don't know why we didn't publish it. I have no idea. This table, I have no idea. Crazy. It shows you that it's kind of complicated. And I think the upshot of all of this is that evolution, right, trying to build these organisms, symbolize a bunch of things to work. Right? A lot of stuff to go into something that has legs and fur. And having a fairly simple algorithm that you do for trees and plants growing that allows for nucleation of the next branching or whatever it is all you need, as long as you start with a heart and a branch. Not too fast, not too slow. There can be a range of solutions to that, right? There's a range of solutions. As long as you start with one big blob and you end up with lots of tiny little ones that fill space. So it kind of relaxes away from like some perfect optimal kind of branching thing to branching is, like branching. That's what we need. It's going to be a network, and because we're big enough for that, we need that. And it's going to branch in a reasonable way. We're going to have a bigger story to go through, which is just going to be geometric. We're going to go through another crazy one. This comes out of a group of Italian physicists who are quite enjoyable, and who had been thinking about branching networks, and then they saw all of this and they said, we can do this better. And then they messed it up in a different way. So it'll be fun. But I think this is a beautiful concept, right? And maybe it sort of seems obvious, I suppose, but no, it took a long time for people to realize that there was a network story here, right? And it's definitely there, but this is a huge mess. Okay, all right, good. So we'll have office hours, we'll talk about things. Okay, so I wanted to show you, here's a little bit of Jeff West. All right. This is a TED Talk, right? TED, which had this sort of great, TED is sort of on the, no? A little bit? We ran some TEDx things here because we're trying to do the right thing, and it was years ago, but then they just like got oversaturated and they went back up inside them. Like it just really was too much. And then there turned out to be all terrible people in the audience, right? That happened recently. I don't know if you know that.
I went to a TEDx talk and talked this.
No? Yeah, no, I mean, it's everywhere. And, you've got 15 minutes and you've got to say that you're going to save the world with, I don't know.
It wasn't even saving the world. One person was just candy bragging about it.
Okay, all right, that works too. They had a big, there's been a scandal apparently, with the bad things that happen at the conferences. It's not the speakers, it's the participants. At the Big TED one, right? The Big TED one is this big thing. And apparently it's just like not good, bad people doing bad things. Okay, that's all I'm going to say. Right. You still have to be invited, yeah. Or pay lots of money, I think. Yeah. I think that's what it is. All right, the surprise. I hadn't looked at it. The surprising math of cities and corporations. It is surprising because it's wrong. So,
that it's very hard to kill a city. You could drop an atom bomb on a city, and 30 years later, it's surviving. Very few cities fail. All companies die. All companies. I must say, many of the indicators look like this is what it's going to look like, but let's talk about it.
I just want you to.
So,
he ties this all to environmental stuff.
10 billion people. Now, these are my comrades in arms.
Here we go.
This work has been done with an extraordinary group of people, and they've done all the work, and I'm the great bullshitter that tries to bring it all together.
So believe people when they tell you things,
I
guess.
This is what we all want.
You should believe people, right? When they tell you things. Okay. Interesting. I haven't been able to watch this. Danforth told me that this existed and that he said that statement about himself. I know it's funny, he's being funny, but that was very accurate, actually. So, anyway, I do think the city stuff is pretty great, though. I mean, we talked about that in Parks, it's cool. It's messy, and people are improving that in various ways. Louis Betancourt, who's now at Chicago, was part of this. That's his thing, really, and he seems a very thoughtful guy, and he's done a lot of hard work there. So I like that. Yeah, I like scaling in general. It's not a problem. But this is a really crazy story we're going through. Okay. Yep. That's good. Let's go to it. Okay, so quick recap of where we got to with this business. So the game is we're going to try to understand the scaling of energy use by organisms, right? And then in that talk, he'll say how this sort of also applies to cities, but not really. Like there's going to be some extrapolation, right? Certainly, one would ask the same questions. How much energy does a city use, and et cetera, right? They do have different treatments. Anyway, so that's the idea. This is sort of left to the side. We're going to have this hierarchical network. We went through the possible things here. I wonder if I get this to work. That's because it's not plugged in. Magic sticks. Magic stick. Okay, so this is the setup. So there was this idea of a hierarchical network. You've got a source. You're delivering to a three-dimensional space, very important. And you've got these destinations that you're trying to leave things at. This could be, you could think of this as delivering packages to people's houses from some central place. I mean, there's sort of, you could wonder how the analogy goes out. But then network impedance, that's got a clear physical story here. The claims with these things these pieces came out that we get the basal metabolism scaling is mass to 3/4, and that we get this fractal scaling, quarter powers. And I do want to set you up with these. I'll set it all up, I suppose, so you can do just the simple calculations in the middle. But these impedances, you put them in, right? We want to minimize those, and we will make this claim that reasonably that evolution has produced organisms with nutrient-delivering network systems that are low impedance. Fair enough. So upshot was that, in fact, if you really, really work through this thing, which no one does, then you don't actually get this mass to 3/4 for this pulsatile flow thing. They don't have to be fractal. They just have to look, right? This is this idea that it just has to look like one big tube from the outside. Yeah. Impedance matching. Go to cube law, that does come out for the outer branches if you use Poiseuille flow there, which is the smooth flow through a tube. And that's, this is a real thing. It's a beautiful, beautiful piece. Amazing. And we got to this result that if you kept going and you sort of just assumed a whole bunch of stuff and pretended and sort of stuck your fingers in your ears, then you could get to this relationship of the exponent alpha and that's for the basal metabolic rate, scaling as mass to the alpha, that it was related to what we'll frame in terms of Horton ratios. It's not said like that in the paper, but Horton ratios, right? So the ratios for numbers of streams streams, vessels of certain orders, and then the radii and the length. So they're put together in these ways. And if you make these assumptions, that there's error preservingness and that kind of a space fillingness that really should be in quotes, everything should be in quotes, the whole thing's in quotes. Just draw quotes. Just walk around with quotes around your head. So, all right, we'll just take that as a given. Actually, if you look at data, this is unpublished. I don't know why I don't know what was wrong with this. But you can see there's some variation in these things, some consistency within organisms, right? So this is the scale, this is the Horton ratio for length. So it's doubling, this is framed in a certain way. If you started at the A order, it would kind of roughly halve in length as you went out through these orders of tubes. But that's different for humans and different for rats and cats that were involved in unfortunate situations. So this paper, I remember, I think this is one where, they filled the rat up with some sort of plastic. It became an X-rat, and then they removed the rat, and then they had the whole network, right? So, yeah. So depending where you are mentally, this is either incredibly interesting or icky and so on, but, but that at least gave them a nice, hopefully imaging, we can get to a much better situation, right? Without having to do that. Okay. So this is a really profound problem. No one has really looked at it. There's just a few papers in the last few years that actually start to look at the statistics of real blood networks, and it's been strangely absent from this literature. With which, you kind of walk away from this at some point and give up. Like the La Barbera guy I mentioned, from what I understand, resigned from the science board, magazine board in disgust, and frustrating. Anyway, beautiful story though. This is a problem. So let's see, so obviously my little scripts are failing here. It wasn't 3 Newberries. So this is an automated measurement thing, right? So this is trying to do something new. This one is, I think that where they start, maybe it's not this paper, they start to look at uneven kinds of branching. So the branching might be different, going in different ways. So, it's more elaborate in that direction. Let me, Newberry's site. Okay, there's that. Okay, so there's a little bit, and this is I'm just pointing to one, and what are they, 2015, and I know I have the wrong thing here, but it's like 2016. So this is just the last few years. I don't know what happened. I don't know why no one has done that. The studies that I cited on that table, these were, individual papers where people had worked quite hard, of course, to do this. It's difficult, and some of these actually have, like in this one, it actually has Tokunaga stuff in it, right? They really went and looked at this other literature and said, there's another thing we can measure. So the side branching in some of these. Obviously painstaking work. All right. This is a Nick Lane writes these great books actually. So, but this is from a few years ago, and it was it's just nice to find someone, So talks about the scaling business in here. I was very happy about it. As so often happens in science, the apparently solid foundation of a field turns to rubble on closer inspection. But it really continues. West is on the TED Talk thing saying it's all sort of true, and even though he tells you he maybe lies. And it's kind of a compelling, beautiful thing. All right. So that's the West paper. I'm going to try to give you something so you can kind of see that it doesn't hold together in an assignment. There are more papers, so let's move on to the next pieces. So this is, again, West and the same team, West, Brown, and wow. Having trouble with that N issue. That's the State of the Union issue is spreading. Right. Okay. So that should be an Nquist. So this is Science again. I mean, these are big time publications, right? So, Science for the first one was 97. That was very controversial. This one should have been much more controversial. They don't really talk about this anymore. This is just not mentioned. They don't mention this. I mean, title, the fourth dimension of life, right? So they went for it. They went for the Bloom thing, which is that 1977 paper. And it is about this idea that maybe, they're full of fractal structures, and they're kind of we're fitting two-dimensional surfaces a little more into, so exchange area here, right? We're able to fit areas into 3 dimensions in ways that when you scale up through organisms, those areas are scaling closer to volume, which is true for lungs, right? Lungs really fill space, even though ultimately it's a surface, right? Okay. They do some very sneaky things. They have biological physical length, so they have number of mitochondria, cell radius. I'm not going to talk about it too much because they don't even talk about it too much anymore. So if you remember from scaling in Puck's Buckingham pie, this beautiful, beautiful thing, right? It's full of that. So it's quite a nice paper to sort of look at because that's just a very pleasant structuring. And then they get area scaling like this. So of course this is going to be D is 3 dimensions. So this is going to be 3/4. Yes. So they do. This is where it sort of falls apart. It all. It's very sneaky. They're going to say that volume is proportional to area times length, which is generally true, right? Meters cubed, meters squared, meters. That's all fine. But when we're talking about fractals, this is a no-no. This is very bad, right? So this thing might be scaling like that. This thing might be scaling as volume. So it's very sneaky. It's hard to unpack this, but that's absolutely in there. It's a direct, we're going to assume this, and then that, allows all sorts of other things to happen. They don't talk about this anymore. It just didn't happen, which is weird. Okay. But, it was sort of an attempt to move away to say it's not just about networks, which is okay, and that this might apply to cells as well, or something like that, which have a different game, maybe. Okay, so this is sort of the history of them. This, again, didn't work out properly. This is a, got to get these things to work. This is a plant, one about plants. I don't really see how it's not super different. Plant site. Sorry about that. I'll fix them up. This is a paper I just sort of discarded in one thing, but I just want to say, so this is science, nature, science.
Their paper is titled Nature.
No, this is a glitch in my ridiculous script.
Almost like us. So.
That's why I'm taking notes. It says in the you're an idiot box over here. Things I've done wrong. It's got, I don't know what it's. No, yeah. Yeah, and then the statement. Anyway, so all right, they got carried away. Okay. Okay, so we're moving on a little bit. So 2004. Personally, I think I said this earlier. It's a very painful thing to be involved with because, beautiful area of science, and you get into it, and it's great, and everyone's excited, and then it turns out to be a mess. And we published that paper in 2001 saying no, we should have Gronk on the front of our paper. No. It's no 3/4. Don't eat Tide Pods as well. Anyway, so look at this. This is really fun. So there's actually a whole issue of this journal, Functional Ecology, was about this thing. They're like, what's good? This is a mess, right? We need to talk about this. So they had this paper, is WBE's model of allometric CI mathematically correct and biologically relevant? See, that was a mistake, right? Because they get to reply, yes. So full points for them. But, titling is a very important titling game. You got to have a strong titling game, and you don't want to leave things hanging around here. You just got to say, no, it's wrong. It is wrong. That would have been good, right?
Or just calling no.
Right. No, you got to say it. Just don't. It's not a mystery. You don't want it to be a mystery thing. People sometimes when they start writing papers as scientists, right? They're like, we studied something. It's like, And the big reveal is going to be at the end. You can't do that. It's not an Agatha Christie novel. It's just like, you've got to tell it straight away. Title, abstract, boom. What you did, make it easy. Anyway, so, that was just unforced error. Anyway, and then they come back, they're trying. This is, I guess it's a year later. Is it in the same one? Yeah, it's a contiguous paper. Yeah, right, exactly. So now, like they're going back and forth. It's like the Simon and, right? It's before Twitter too, right? So, what was that?
Now we just hash out on Twitter.
Yeah, some hate. God, I saw some more academic tweet rage I was going to show. Anyway, but someone called someone a hater. You're just a hater. It's like, okay, you're just a hater. They spelled "you're" incorrectly as well, so that was bad. What's up? I guess I'll bring that one up at another time. But it was to do with Taleb. It was to do with the Black Swan thing. This is a very dangerous territory, and I feel like I shouldn't even... Because Nassim Taleb has a huge following. If you go and look at his thing, people really love him. A lot of the discussion is about deadlifts, which is interesting. It's a little bit male. But if you don't deadlift, you're not worth your existence. You're a waste of space, I guess. There's a lot of discussion about that. It's a lot of righteousness, and So. Yeah, but I was basically saying that Black Swan is not a good encapsulation of the thing it's trying to describe. It's fine now because everyone just says Black Swan, right? And they sort of know what they mean. But Black Swans, and I know this is a deviation, but Black Swans are, it's true that, so I come from Australia, right? And Black Swans in Western Australia, they're not that surprising, of course, because you're from there. But if you're a European and you're sailing around the world and with questionable legal intentions, and you come to this place and find kangaroos and then platypuses and all these other things, it's not the piece you would come back and say, hey, we found some swans that were different colors. Like, it would be not the first thing on the list of weird things you found in Australia. Anyway. Okay, so here's more work. This is 2010. This is published in Nature, which I don't quite understand. It's a fine paper. I just don't really know why it was in Nature, really. But then, so they say, well, let's just make a quadratic. And I apologize, that should be, I'm just adding some more stuff here because it's madness. This should be squared, of course. This should be brackets around this thing, right? And they say it's a better fit if you use a quadratic. So that's that blue quadratic. They didn't include the elephant or the orca. Apparently someone got in with an oxygen thing and measured how much an orca was using. I don't know where that came from. That's amazing. It does seem stupendous to measure the metabolic usage of a whale with teeth. Right, okay, so anyway, so they got a better fit with this, right? So this is, and then it deviates at this end, and then they kind of like argue about whether the thing is 2/3 and 3/4. They do this sort of thing. So I showed you this regression where you start from the bottom because things got bigger, and they show that the fit is like there's 2/3, and then it sort of falls apart. So it's sort of a similar story. And then they have a thing. I guess that's what this is. If you regress from the bottom, and this one is where if you regress from the top down, which is right, you start with the biggest one and then open a window going downwards, then you get a different thing. And I guess they're trying to say that it's messy, which is true. But that's sort of, my argument against this is a while ago, right? I remember having this discussion with, like, why would you measure from the bottom? We absolutely have a zero, right? And then we start and we grow, and evolution produces bigger and bigger things. There is dwarfism, right? Things get smaller now and then, but that makes sense, and evolution is producing things that have bigger and bigger structures, and they're fighting against gravity in interesting ways. So you can imagine the deviations could happen at that end. Anyway. Right, fine. But that's 2010. That's got 300 citations. It's done well. This one is asymmetric networks, right? Okay. And then there's still, so this is really weird actually, because you have, people just keep going back and forth. That's 2017, and they say, oh, we show the three-quarter thing is okay, actually. Whereas, if we go back to this one, they're like, where's their citation? Yeah, they're right. Sorry, I put the citation, the quote at the top. This raises the question of whether the theory can be adapted to agree with the data. And these are people from the team, right? The Quarterology. These are people who have left the cult, but their cult pulls them back in because of funding, maybe. Anyway, so this is really just nuts. So Wes now has a book. This is really wrong with me. Of course, there are beautiful reviews, full of intriguing big ideas, but amazingly sloppy. I'm just taking Amazon comments, which, book is terrible, bidding is terrible. It's true. I mean, this is really amazing, right? And I think this is probably taken from the Betancourt paper. You have, you actually plots with different scales, and it's not clear if they're log, and log E, or log 10, or whatever. High quality Amazon reviews, really good. What's that? So they're not really, right, because they study corporations and cities and organisms and talk about the differences between them. So he likes to point out that cities never die.
But they do.
How do you feel about that? Right, so the claim that cities never, that's what they say. Corporations, are very new things too, actually, right? We didn't really allow corporations to persist, until the 1800s, They'd always be dissolved. Because you had a king and, it's kind of obvious it would go wrong. Corporations are weird because, of course, they merge and they change names and so on, so they're pretty stable. I mean, of the biggest cities in the world, a lot of them have persisted, but certainly they've gone through different. They haven't all just been going like this. And at the edge of things, ghost towns, right? I mean, famously, right? Things evaporate on the edge of it. So that's not a city, but in terms of human settlements, things.
I mean, is he talking about modern cities?
It's just big city, like any big.
Any big city for all of time?
Yeah.
But it made more sense historically because there were geographical concerns for where you build a city. When you look at things like Istanbul,
Yeah.
there are places that
So trade.
are geographically advantageous.
Yeah.
So it keeps capturing them.
So there's trade. There's of course, if something really enormous happens in terms of water, right? The place dries up, then whatever, for whatever reason, then people will simply have to leave. Southern California is fighting that eventuality. What's that?
And we have Las Vegas.
Wow,
You're relevant.
just amazing. It really is incredible. Yeah, the shots from above, right, like Palm Springs and so on, it's just green lawns and then desert, It's amazing. Yeah, where I grew up, there were no rivers, right? There was no water supply, right? So water was very, very scarce, and you could bore for water. It was pretty deep, 400 feet, and that was good for sheep and so on, and the garden. But the water we drank, is from the roof, right? From just rainwater, which is illegal in some states in the U.S. to drink your own rainwater. I think it's not for health; it's because someone else owns it. Is that right? It's so amazing to me. What an achievement of something.
But it does have like different acidity.
Yeah, it's awesome. No, I'm just kidding. I don't know. That was water in a particular part of the world. Yeah, you wouldn't want to drink some water, right? Obviously, yeah. And then a possum dies in the tank, and you're in a lot of trouble. Real feature of rainwater, I'm afraid. It's not good. Yeah. So, and we got 18 inches a year. It's not much. So you have to move water sometimes. So I'm just like, my mind is blown by the Southwest. I'm just like, oh my God, this is just a precipice of disaster. Well, sort of the Anasazi Indian people that right in New Mexico seem to have had this, right? The Pueblo, were very interesting, beautiful, fantastic, right? And then just vanished, yeah? Like Mesa Verde. And it seems to be drought, I think. Yeah.
Those dwellings must have relied on some water
Yeah.
source.
Yeah, because you're not going to, right? It's not, there were no, right. But it was a mystery for a while, at least for us looking back, if it was war or something, right? Whatever happened, or migration, and then eventually it does seem to be from records that we've been able to kind of figure out that there really was this 30-year drought. Yeah. Yeah, I mean, California started to get into trouble, right? 3 or 4 years of a drought, and it really actually was interesting to change people's behavior, right? So, yeah. Well, that's an interesting flip. People actually started to, like, if you see someone's watering their lawn, there was hate, Okay, I know. All right, so let's step away from the West madness and venture into another team's insanity. So this is Banavar and company. So Banavar might be UPenn, and there's a bunch of physicists from Italy involved. So this is a interesting, different approach, right? So we're not even going to think about fluids flowing through tubes or anything. This is going to be much more abstract, which is a good thing to do. And the idea will be there's some sort of source, which is here, and it's trying to distribute material out to all of these sinks. This is taken straight from their paper. You could have this kind of braided version, and of course that's what we've sort of been talking about, these sort of different possibilities of braided versus network structures. Braided again, this would be like a pure branching network one here. And then the idea of this is say, well, you could do this as well. This is obviously incredibly inefficient, but that, you could make that your way of distributing things. I guess it's a number of steps that they're showing. But if you think about the flow here, there's going to be a lot coming through here, and there's a little bit siphoned off here, a little bit siphoned off here, and that's the way to think of this. All of these have little sinks, right? Just like in the problem, the simulation you're trying to make with from Magnasco and Bohm. There are little drawers coming out, right? So that you imagine these are all the little capillaries or whatever it is, but they're trying to be even more general. So this is actually, we ran a seminar at MIT in '98, and Ronaldo, who was part of this, was there. He's the guy who played rugby for Italy, and he was spending a semester or a year at MIT. So he would come to our meetings, and we kind of picked through the West work and kind of, showed that it wasn't working, and he was just sitting there just getting very excited, and it turns out, they'd been developing their own story. Ronaldo is behind that optimal channel network stuff that I showed you, just talked about a little bit for river networks. So they'd done a lot of work on landscapes and trying to figure out how all of that worked. Tide. Okay. And so they went for this thing. All right. So the plan for them, so they were able to show, so it's always about this dimension thing. They claim to show, and this is a Nature paper. To be honest, so what happened was they presented, and I remember I did some analysis, and I went over to Ronaldo, and I sat down, and I was kind of worried about this, and worked through showed him there were some problems with it, and he said, well, he would come over. So he comes over to talk, and he walks in and says, it was been accepted at Nature. I'm like, oh no. And then we spent 2 hours at a board going through how there are some problems. And he says, okay, I'll go and talk to and they decide not to change anything. Anyway, so, and then they have their own follow-up papers, which are really, where they basically admit there are some real problems. And here's the big one that's sort of sneakily in there again. This is where they have a volume of the network is scaling as mass to the d plus 1 over d. So for us, this is 4/3, right? We're in 3 dimensions. So that is not good. You've got superlinear scaling for an internal structure. It's going to explode. So here's an estimate. 3 gram shrew, 10% of its body is blood, which is roughly true of organisms. Then you would be in this case. So that is not good. That is not good. Also not observed. I mean, there is actually a paper, of course, you can find where someone has measured the volume of blood in organisms across scales and found that it scales as mass to the 0. A mass to the 1, yeah. What I said was silly. The ratio is 0. Okay. So it's pretty obvious, but again, it's sort of it's a tricky thing because there's this tension between, there's a capillary kind of thing or a destination or a sink, let's just say sink, and it services some volume. And there's this elasticity in how that volume can scale, right? And what they actually do is they grid it so that these are really actually fixed. There's no flexibility in these things. They just say it's supplying sort of a, that each capillary, independent of body size, services the same volume. All right, so there are details in there, but oof, it's a tough one to get into. But they have a paper in PNAS a few years later that says, ha ha ha. Of course, that's not right. Let us add some more, let us do some things in a bit of a different way. Oh my God. All right, that's our elephant of sadness. Okay. All right, so I'm gonna take you through, and this is just incredibly mad, but let's sort of talk through a very simple thing, which is derived from all of this, and actually comes out of teaching this course, and like going back to these things and thinking about something, some simple ideas. So I think the key thing is we're going to have d-dimensional, a d-dimensional ambient space. We live in 3 dimensions, and our sinks, our capillaries are in filling a 3-dimensional volume as well, right? And that's true as we go across organisms. But if we think of something like a network that's actually in a 3-dimensional space, right? There's height, right? So they can get deeper and so on. And when we look from the above, we're not really worried about it too much, but that's true. But it's really a 2-dimensional, it's a little rough and so on, but it's really a 2-dimensional thing inside 3 dimensions. So that's a key piece. That will mean a lot later on. So we're going to assume sinks are invariant. So we're going to use a lot of the things they've done in these other 2 papers, or these other 2 lines of work, I should say. There's some sink density. So this captures the idea that maybe for elephants, the capillary is servicing a bigger volume than it is for a mouse, and the whole thing runs at a bit of a slower rate. Ben, who was in POX last semester, gave his students in calculus a question, and it was about the fastest speed, right, that I showed you again for the scaling of organisms as a function of mass. And the students were able to figure out that a 0 mass animal maximum speed is 0, because it doesn't exist. And then in the limiting case, and the infinite mass one just never starts. So, yeah. So it's good. Math. Right, but this is, that sort of fits in, this idea that the bigger ones, it's like harder for them to get everything running. Okay. There's going to be some cap, the flow of speed of material, right? That's not going to, you can't have that scaling in some way that will go through the roof. It could increase, but not scaling, right? And we'll try to take this network as a bundle of virtual vessels, which we know is not really true, but this is just going to be an abstraction. So here's a heart supplying these 3 pieces, or whatever we think is our source, applying to 3 sinks. And so this tube, or the amount that's being delivered here, equal amounts being taken that's being siphoned off here and here and here. So you need, whatever it is, 3 units per time coming down to this first one. They split off, so 1 gets taken in, 1 gets taken in, 1 gets taken in. Fair enough? So we'll just say this is actually a network that's structured like this, that it really is these 3 little pieces, and they're just packaged together. And we're not going to worry too much about the fact that we're away from a braided structure. We know that actually there's goodness that comes from the material being combined together, right? Less impedance and so on. I mean, it's sort of funny, right? There's the less impedance, so you want networks make sense from that point of view, but also just like you would never be able to get you have to have some pretty, okay, so what you could have is like a little tube from the heart to every capillary, a separate one, right? Just be like this whole bunch of tendril, it's pretty yucky, but this whole tendril-y thing, and each one has its own little tube, which an engineer might make or something, right? I mean, you sort of could do it. And so you'd be delivering all these little blood cells, and it would be just a disaster. So, all right, evolution's not going to produce that because, So, number of sustainable sinks, how does that scale with volume V? So you're increasing this thing, there's just a single central source, so that's an issue, right? And as you get to higher and higher dimensions, you're going from a zero-dimensional source to 1, 2, 3, 4. That's a harder thing to work with. And what's the highest scaling we can get for this? The number of sinks is a function of volume. That's what we want. Right. So there's a really beautiful thing I think that's going to come out with surface area and network structure. They're going to match, only in one special way. That's going to be 2/3. But, for some reason, a lot of those papers I just showed you, they don't talk about the bird stuff, right? The bird scaling is super duper 2/3. So, what's going on? I guess someone's trying to invent a 1,000 kilogram bird so they can show that it deviates in scaling. All right, so let's imagine we got a family of shapes, and they could be all sorts of shapes. We're just going to do it pretty generally. And here's our splattered eggy thing. So it's going to scale allometrically. So we're going to have 2 length scales for this one. And this omega is going to represent this shape, and this V is a parameterization, which is, so it's in general, right, it's volume, but this is area, of course, for 2 dimensions. And then we're going to have these length scales. They're going to scale the overall volume to some power. And because, right, as we multiply length 1, in this case length 1 times length 2, we need that to be proportional to volume, as with scaling. So these exponents have to add up to 1. Right, so if it's isometric, the exponents will be this length scales as area to 1/2, and this length scales as area to 1/2. For 3 dimensions, the lengths would scale as volume to the third, volume to the third, and volume to the third. And that's what this is. So for isometric growth, we'll have 1/3 for 3 dimensions and 1/2 for 2 dimensions. They're the ones we're mostly going to think about, but in general, it's 1/d. And for allometric growth, you just have to have 2 of them different, right? Some separation away from 1/d. So there are some interesting extremes. Here are the extremes, right? Yes, I have to do that. The spherical. That's a hilarious joke. Assume spherical cow. Yeah. All right. So here's our scaling. So in this case, we have the 3 length scales, right? We orient some lengths, like an axis around it here. The 3 leg scales are going to be scaling as volume to 1/3. And in this case, there's going to be, let's just make it like this. We're making a pancake cow, so it's just instantly delicious, right? Yeah. So the burger cow. Yeah, that would be better. Or it could be a tofu burger, that's fine. So it's got some thickness, but it's just, and that doesn't grow. Or you can imagine it just grows very slowly. It doesn't scale, logarithmically or something like that. But these are, this is an important scientific piece, right? Okay, so these lengths are going to scale. So in this case, they'll scale as volume to 1/2, right? This is going to scale as volume to the 1/2, volume to the 1/2, volume to the 0. So this one times this one times this one gives you volume to the 1/2 plus 1/2 plus 0. So volume to the 1. Coolness? So it's cool. Yeah. And then you want to think about surface area for these things. So surface area, in this case, is going to scale as volume to the 2/3. But this one, the surface area, is going to scale in a different way, and it's going to be, and this is actually a problem that was in Parkes, but it's volume to the power of 1 minus the minimum scaling exponent. It's a nice thing to figure out. right? So the surface area around here doesn't really matter. It's dominated by the fact, that this is the slowest scaling, and in this case, sort of a non-existent scaling. The surface area, because these two length scales are scaling like volume to a half times volume to a half, and that's length 1 times length 2, that's the surface area, right, for this thing, yeah? Plus, length 3 times length, you don't have to worry about that one, right? That's not it's going to be insignificant. But so in this case, surface area is actually scaling like volume as well. So this is and then you're going to have some network in here, right? And it's just like increasingly disturbing internal aspects of this cow, right? So there's going to be some heart in here and some udders. The whole thing's a mess. Anyway, but it's going to have to spread out like that, which you can imagine, so for a river network, that's kind of what's sort of, right? We're going to have that sort of thing. Or a city, you can imagine there's a city here and we've got to get everyone inside. Not a cow. But you have your city and you've got people trying to get in. That's a kind of a common kind of thing. And your city is growing, or you have a collection of cities. Yeah. So that's a pancake cow. All right. I made the important tarot cards. Okay. So I just kind of told you, but it's a nice little thing to think about. You can actually just, you can do it abstractly, or you could think of parallelepipeds, right? You can make yourself little rectangular blocks. Okay. A tofu loop, right? Okay. And then, so this is general families of regions. How does this work, right? Okay, this is good. Okay, good. So it's going to matter. So this is consistent with what Bannevar and so on. I mean, it's just an observation, really. Like, if you want to make the best and worst kind of networks, and I sort of alluded to this before, if you had your own little, private tube that took you from downtown Manhattan to your house, and right, and you don't have to be with everyone else in the subway. Or, you can be in your little special car and so on. We sort of do it with cars, right? We sort of do it. But the traffic will actually affect you, and you will be rude and sad. But imagine you have your own tiny little tube, and you get in and you go, whoop. Okay. So we could have that. That would be sort of our best configuration, right? This will be a disaster, and it's kind of like the same thing where you travel, you basically fill space. You travel everywhere before you get there. This is your random walk sort of thing. And this could be constructed if you say, I'm actually just going to have one person deliver everything and they have to walk to every place, right? That would be a terrible idea. Which happens with school buses, though, a little bit, right? So, you have your school and you have to get dropped off. So the bus has to go to all these places. Okay. Which is really tough. So, when I was a kid, actually, it's like 15-kid elementary school that I went to. In the morning, really early, it takes 3 minutes to get there because we were the last ones picked up. But after school, we drove around like 20 miles or something, and then we were the last ones to get off. Never really thought about it too much. Okay. So, there's this very clear statement. The minimum network volume you could have is one that's proportional to all the distances from the source of the sink, right? We have all these little tubes that they're delivering. They're all the same size. They're not really, growing or changing with overall volume. The elephants, you're trying to get the same amount of stuff to a capillary. Capillaries are capillaries. Humans in their little cars are humans. So this statement is clear. That's the best thing you can do. And in fact, this is Gassner and Newman, which we talked about in POX, but it's just quickly again. This is taking a real network. It's the T is kind of in here, and then this is the commuter rail network for Bostonian peoples that's out here. So, if you want to get from one place to the other, that's a bit tricky if you want to stay within the commuter thing, but of course, if you're trying to get to the central part of Boston, then it functions quite well. And this is where everyone has their own special little, right, thing. Boston is a bit funny too with the T because there's the red line and the blue and so on, and the green line has the little splintering ones, right? It has the little smaller ones that do actually kind of break off. So they have sort of a mixture of solutions. they've done a couple of different things. This is a minimum spanning tree, which is just a bit of a funny thing to do perhaps for this, but like this one got broken off. Right, no loops in that one. And then this one is the work that they do in this model to sort of construct in this paper to construct a minimum one. And it's quite good. It fits this pretty well, right? I mean, there are wiggles because of the way things got built and there's geography and so on. And these are just going to be straight lines. But the point is the one that Boston actually produces is pretty efficient. So equations can do it. Slime mold can also do it. This is a science paper, just great achievement by humanity here. This is a Japanese group. They put down a little station. They made a little a plate that has locations of cities or major stations around Tokyo, and then put a slime mold in it, and then put the food there, right? And then let the slime mold grow. So they put food at the stations, let it grow, and then it thins out, and it's like it's a blob to start with. Slime mold, which I guess is super interesting, but it's not a, just doesn't, I mean, it's super interesting in its, it needs a better name. And then it thins out, right? Yeah. And it actually fits, it conforms pretty well to rules for biologically inspired adaptive network design. Excellent. It's pretty interesting, right? So it's trying to feed itself and do it in an optimal way. And it works out. Okay, so there's a video you can watch there too. Yeah, fun. Okay, so here's a simple, look, so let's try this. We're going to imagine a little bit more. We're going to say, here's our source, and here's our sink, and we can imagine that maybe the tube changes in size, right? So, and the reason for doing this is it's going to come fast out of here, kind of shooting out of the origin, and if this was a fluid, then it slows down because this widens up. And this is very exaggerated. This is true, actually, basically what does happen in the blood network, because it's slower at the outer branches. And so that's one way to just build it in a geometric way, where there's no physics in this, but we could just say, so that might work. But this can't really scale with size in a way that matters, right? If you can play around with this and figure out what the volume of these odd shapes are, and it's not going to be something that contributes, right? We could try to put in a scaling so the radius is tapering from the sink, where we know what the sink is. We can imagine the tapering, like we specify what the outer part is. We want it to be going at a certain speed here. And the volume was going to scale as length to 1 minus 2 epsilon, or 1, depending on how epsilon is. So there's some nice little results in that. It's really detailed silliness, I suppose, but it's there. Yeah. Right, so for large enough length, it doesn't matter in this case, but there is a minor scaling if epsilon is less than a half. Fine. So then we set this up. The minimum volume, we're going to have a density of sinks across our shape. So this is a function of x. And then for every one of these sinks, just like that slime mold or whatever, every one of these little places that we're going to, or the commuter stations, we say, okay, this is the volume of the special tube that goes to that sink. Right, it's a sort of funny fluted thing, or you can imagine just a straight straw, but we're kind of imagining a more general thing. That's the volume we can put in there, right? And this is for epsilon less than a half. If you do this calculation, and you can do this for arbitrary shapes. It's a nice little it's a nice thing. Then you end up with this result. So this is going to be the minimum of the volume is going to scale as density, and then the overall volume of the shape, right, as 1 plus, and so gamma max is going to appear in here. The maximum scale is going to appear in there. So that's a cool thing. And if epsilon is a bit higher and we don't have this, then we end up with this network volume of scaling as rho to the v, right? So it's density times the volume. Good. good. Now, that scaling's not really going to be an issue too much, so if epsilon is 0, then the really big result is here, I think. So it's going to be density, volume to the 1 plus gamma max. So this is where the allometry of the shape comes in. The network is trying to supply this thing. We're thinking about this shape over many scales. The network required to, so what this is saying is the network, so gamma max is here. This is going to increase, right, as gamma max gets bigger, which means it becomes more of an, further away from being isometric, more allometric, right? So the pancake cow thing will have a half here, and the spherical cows will have a third here. So the pancake requires a bigger network. The scaling of the network has a higher exponent with respect to the volume of the thing it's trying to feed. Right, so it's less, it's more costly in terms of infrastructure. Right, so a bull is easier to build networks into, and you have to be careful about thinking, because you think, okay, it's a bull, but you have to think about how it scales, right? So as we move up through bigger and bigger spheres, the way the network scales, the minimum, this sort of optimal network's volume, the way that scales is as low as possible. If it's a series of pancake shapes, then the minimum network that you need to supply everything, it scales in a way that's a higher power of the volume, right? You need to make more network. Eventually, you'll have more network, right? Okay. Yes. Oh, okay. Okay. So these are these pieces. So scaling is isometric. Then we have this. We put 1 over d in there. If scaling is allometric, we're just going to say gamma max is this gamma allo, just like whatever it is, it's greater than 1 over d, it's larger. And this is this point I just said, right? So that the minimum network's volume for the isometric one versus the allometric one, that ratio goes to 0, right? So this is as we go up through volumes. So you need less network to supply a isometrically growing series of volumes. Okay, good. We're gonna make it. Caffeine is not wearing off. Okay. We can worry about this one. So the network volume it's not even dependent on the overall shape. Don't worry about that. So what we're gonna say is that epsilon is gonna be close to 0 for large enough scales, right? And this is because that tapering is never gonna get down to some ridiculous limit. You still got to put stuff in through it, and it's also just not going to be that fast, right? So kind of went to this effort to make these to sort of incorporate, allow for the possibility of scaling in the tube shapes, but in the end, it's, we can sort of make the argument that we might as well just have This may all be about tide, I don't know. You can straws will be fine. All right. Milked it pretty strongly. Okay, so so here, let's talk about blood networks, and maybe I can get through this now. Okay, blood networks. So we're going to say, right, the velocity of the capillaries, it's not going to go out of control. Certainly at the capillary, it's sort of it's nice and slow. The aorta, it can't get too fast. Things are going to explode. Material is going to be costly, so you certainly don't want to have a ridiculous network, right? So you're going to make it fairly much like this Gassner and Newman thing for the Boston commuter line, and so on. You want it to basically go out to the capillaries as reasonably fast as possible, right? It's not going to do some loops and then run out. Some weird things up here with the circle of Willis. The term for these shapes, by the way, is star convex, which is a thing. It just means that there's one point where the heart is that you can directly see everything in the shape. They're not actually just convex. So, cardiac blood networks, they fill a d-dimensional volume, and we're running around in 3 dimensions. This is well known, right? I mean, just by looking at organisms and also someone actually trying to compute it. This is a paper by Stahl. The volume of network scales as volume, just does. Right. So sink density has to therefore decrease, right? Because we've got these two things. The volume network has to scale as the volume, but we've got this for our best network. So this is an argument from the network. This is an argument from reality. So the density of sinks has to go down for this to be true, right? This is actually scaling a bit faster. So this is v to the 4/3. So we'll need I said the wrong, yeah. So we'll need a minus a third, right? So from this very simple model, the density of sinks has to go down for this optimal network. Yeah, that's a good thing. So that's a result. And then the rate of overall energy usage, right? So it's going to be the density of sinks times the volume, which volume we say is proportional to mass. And so all of that comes out to be d minus 1 over d. And so for three-dimensional things, we have 2/3. This is a purely geometric argument. Oh boy. So, it's possible you could get a higher exponent, less efficient thing, I don't know. But here's the thing that's never really said much, is that 3/4 is not great, it's higher. It means that these organisms are not, this is not when they're performing at their maximal output. This is supposed to be their basal energy metabolism. So you want that to be, you want it to be efficient, right? So this is what we would expect from that kind of simple, scaling of surface area story. But now this is a network thing. Now it's a network thing. And in fact, this is quite a nice result, right? So as we had, the number of sink scales is volume to the 1 minus gamma max, right? So for isometric, it's volume to the 1 minus a third in 3 dimensions. But for, say, our pancake ones, it's going to be volume 1 minus a half. It's volume to the half. So the metabolism will actually scale as volume to the half. You're not going to have, right, these pancake cows, their metabolism is actually going to be lower, right? They're going to be lower, but they're going to have this higher surface area. So they're going to be like, it doesn't match. Their surface area will be scaling as volume to the 1, and their metabolism, if you like, or their sink is going to be scaling as volume to a half. Not good. And the only place that you get this this thing matching with surface area is 2/3. So this I think is a profound thing, right? And so here it is, right? Surface area is 1 minus, it's volume to the 1 minus gamma min, and the number of sinks is volume to the 1 minus gamma max. So they're only the same when gamma min is gamma max, and that means all of these exponents are the same, and that only happens when it's isometric. So this is, look, the idea of this, it's evident that right, we have a network that's supplying nutrients in all these organisms. Thinking about the constraints on that is incredibly reasonable. It's a good thing to do. And, if you strip all of this other stuff away, you do, I think, get this rather quite beautiful result, that the most efficient network, in this very simplistic thing, this most efficient network will match with the surface area scaling. These are two very different stories. They only match when we have isometry. Yeah, the pancake ones would lose heat too fast, right? And so they wouldn't be able to keep themselves warm. You'd have to make special, Etsy would have to make special cardigans for their pancake dogs. We definitely have pancake dogs. Not cats, you couldn't do it with cats. They would defeat it through treats. Okay, so I don't know, I think this is quite a beautiful thing. And there it is, yeah, right, it's right there. 1 minus gamma min, 1 minus gamma max. Okay, tarot card, yeah. So as we've seen, the exponent, it works pretty well up to maybe 10 to 30 for mammals. It's great for birds. It's madness, the whole thing is madness. Maybe there's a different kind of scaling, and there's another paper, it just came out, I didn't put it in. But so instead of, say, this quadratic fit, which is a pretty crazy thing to do, like that's just not founded in anything. I mean, it's mathematically you just do it, but quadratic fit in log space. I don't even know what, yeah. Because I mean, I think you end up with mass to an exponent and then mass to another exponent times log of mass. That's you'd have that correction in there. Okay, is that right? Yeah. And we have this story, right? This breaking scaling from this economist paper. This is from a long time ago. And I know I've repeated this slide. I shouldn't repeat it. I did say recall. Good. Yeah. Self-awareness. Maybe it's good. Yeah. So like I was trying to say, that there just now. So this one, and then another.
This is an interesting thing. Let's go to the surface, and finish up what you got. Energy expenditure. This is Stefan Boltzmann Law, famous thing from physics. So this is the amount of energy given off by a shape, by some object. Exchange with its surroundings based on radiation. And this is the prefactor is very much roughly 10 to the 5 to the regression, right? This is in ergs per second. And this is like sigma is a I can't remember what's in sigma, but it's the Stefan Boltzmann constant. We're going to put that number in. We're going to put in some rough ideas of scaling and so on, and we can get this estimate out. And in fact, the regression gives you this. So it's pretty good. It's not bad. Heat's given off in a number of ways, but certainly radiation is a big part of it. Again, that's why they can find you at night. So even that works pretty well. Okay, so I think I'll talk a little bit more about it on Tuesday, and then we'll move on to some other things. I guess I want to recap briefly the facility location thing. I just want to, I know you've seen it, but I just want to go through it again quickly, and I'll point to the stuff we did in parks, but just because it's sort of part of this package, I just want to sort of highlight what's in there again. Where do you put your Starbucks and your hospitals and those things? Just such a great story. And I'd hope to have the next piece for you, right? But we're getting close to the connecting that with the hot model and some other, and all of machine learning. So there's that. That's really exciting. But then I think we'll move on to some other pieces, and the next thing is random networks, which is a beautiful, rich area of things, just a good thing to know about, and some really fun little mathematical pieces with generating functions and so on, and bipartite networks, such a profound reality. So we'll do some of that, and then we'll find our way into some other tarot card space. All right, but it's madness, and hopefully I've conveyed that in a way that you believe me. I am the unbeliever. All right, thank you. Right. I'll leave this other piece out. Okay. Good. All right, so now we're awake, sort of. Yes. Hopefully this will work. We've had explosions. Okay. So we just got to, so this is argument that, that this is our sort of main result from a really simple argument. That if we have, and this is a basic thing, right? We have bodies, and they could be 2D things, 3D things, they could be living in higher dimensions, and so the big distinction between, say, branching network structures in 2D, like river networks, is that it's a two-dimensional surface that's being drained, but it lives in 3 dimensions. I mean, this is an obvious thing, right? So you can have rivers getting deep. There's a 3rd dimension for them to grow into. But bodies, 3-dimensional bodies with a network supplying sources and, sinks, capillaries, if you like, we live in 3 dimensions. So there isn't that ridiculous 4th dimension to grow into, right? So we don't put that in titles or anything. Okay. Really embarrassing. So this was the result we ended up with, right? So this optimal network where basically, you know, the tubes supplying things are going as straight as they can. There's good evidence for that anyway in the real world. Grows as density of, these are the sinks, right? Or times the overall volume of the shape that you're trying to supply. And then we had this really, so we're going to not worry about epsilon. That was an extra argument about scaling that said that the tubes could potentially scale. We were just being careful, but basically it's 0. And it's going to be this 1 plus gamma max. So gamma max again is the exponent for the fastest scaling dimension. And so for isometric objects, we have gamma max is 1 over d, right? All of the scalings are 1 over d. And if it's allometrically scaling, then at least one of them they'll be different and be greater than 1 over d. All right. Which means this volume will scale a little bit faster, right? That's going to be a larger number. Okay, so we talked through this. There was the matching. I'm going to skip through these pieces. There was the matching. This was this kind of big result. And I know I sort of threw this question into POX in the scaling section early on, which you may or may not have seen because some of you are from different POX versions. So the surface area scales as 1 minus gamma min. And this sort of metabolism, which is we're going to say is the number of sinks, right, that you can supply if you kind of are running the same system, right? You've got the same kind of thing. You've got blood in all of these different organisms. You're not changing that plan. You've got the same stuff. Then that's going to scale as, right, and you're not changing from like walking to cars to subways to whatever, right? So then you can kind of get around things, yeah? But we've got the same transport idea. I mean, it can go faster and so on, but there's a limit to that as well. So number of sinks scales in this way, and these things to match, for these things to match, gamma min must be gamma max, right? So the smallest scaling must match the fastest scaling, and that means they're all the same, all the exponents are the same, and we have isometric scaling objects. So that's a beautiful result, I think, very profound result. I'm going to say it. Gets a tarot card with little proportionals. And then we looked a little bit at this. So there are a couple of things here. There's the exponent, you know, sort of just recapitulate this as a recall that the exponent matches. I mean, it's spectacular for birds. I mean, it's kind of crazy to me that people keep talking about this. It's totally crazy. And Stefan Boltzmann, right? This is a really beautiful, amazing physics story that, you know, we give off heat and it scales with our surface area. All right. Okay, so that works there. So the thing that happened there was the density of supplyable sinks went down. So that's the important thing. So because the volume that's being supplied didn't have this extra way, there was no other kind of way for your networks to get thicker, right? There's sort of a limit to what they can do. They've got to fit inside this thing they're supplying. Yes, of course. Then, but if we were 2D organisms running around, but we had this sort of third dimension to kind of grow in, like the tubes that supplied us could kind of have a thickness and they could grow, then we'd have different potential scalings. And that's what you get when you look at something like river networks. So we can sort of think of one big basin. We have many like sources, and now the sources are just, you know, it's raining, if you like. I mean, sort of on average over time. And so the sources are somewhat uniformly distributed now, right? It's not like you go to a bigger scale and there are less sources, right? So this is not happening here. So we're going to have sources, the density of sources is going to be roughly constant. So again, we have this general story, this volume of the network. This piece is going to be constant because we had capillary density going down, but for rain falling, there's no sense that this is really changing much. I mean, this weird fractalness and so on to rain, right, and clouds and things, it's true. But you know, big enough scales, basically all right. So this is a two-dimensional surface, so little d is 2. The ambient dimension, big D, is 3. So we put our 2 in here, and we get 3 over 2. So we get volume as 3 halves. And there's no way we can kind of offset that, right? What we did before was we had kind of basically a 4/3, and then rho had to scale as volume to the minus 1/3, so the volume of the network would fit inside organisms. But we don't care about this now because this can scale faster than that. Okay, what this is now is this is area, right? This is basin area, right? It's volume in 2D, this is basin area. And the volume of the network can scale faster than that. That's okay, right? So because there's this ambient dimension that's greater than the dimension of the shape that's being supplied or drained in this case. So really area, so this is all okay. My little pointy thing. Right? Landscape's a two-dimensional surface. I mean, I'm not saying anything profound there, but they're living in 3 dimensions. But that's the big difference, right? This is 3 is greater than 2. That is the big piece here. And 3 equals 3 for volume, for biology. So they can grow in width and depth and so on. That's often not in a lot of these big picture kind of laws we look at, but there are some potential scalings here. And we don't have to worry about that too much. All right, so let's look at actual data again, very dangerous. So, the volume, it's like the volume, so you imagine your little artificial networks that we make, these little pretend ones, or you could take a real data set where we've constructed the networks, and we know that that's a complicated, messy business, but we have this satellite data, it's on a grid, right? We're not, it's not perfect, but it's a bit of a messy thing, and we get a network out of it, and then we just put pretend rain on it, right? And let it just sort of fall down. And, right, so at any given time, you've got some basin, and there'll be all of the rain that fell, at different points back in time will be just leaving now, right? So the rain that fell, 70 clicks before will be now exiting here because it's like 70 little hops down this thing. And the rain that fell 3 clicks will be, ticks ago, will be coming out now. But basically that whole area will be going every time that will be coming out of this piece. Okay, so, but that means everything's kind of stacking up everywhere, right? So at the start of a stream, there's just going to be, right, it's going to fall in, rain's going to fall, and it's going to drain out straight away. Rain's going to fall in straight, but it's going to start banking up on the next one, right? Because down here, there's one little drop of rain falls at the outlet, but all of this other stuff is coming through it as well. So it's all being integrated. And so the volume of the network, in a sense, from these little artificial, so either it's a real surface or it's an artificial surface, but we kind of artificially rain on top of it, will be this. So you just sum over all the drainage areas in your volume of network. And I won't go through all this because I'm belaboring things, I suppose. But Hack's law was this story, right? So that's this kind of, that's the 3/4 Lorry area here for networks, for river networks, if this H is greater than a half, right? That was this sort of something weird is going on story, and maybe there's some massive conspiracy of universality in physics that we don't understand. Okay, so if that's true, then you can figure out with Horton's laws and Tokunaga's law and all this, sort of play around with them, that the volume of the network actually scales as area of the basin to the 1 plus H. All right, so you go through, do all these calculations, connect these things. I don't think that's published. Yes, it is. Of course it is. What am I talking about? Yes, yes. Maybe not the explicit details. Okay, so, and then these calculations we just had, that 3 halves means that this is a half, right? This is going to be little d plus 1 over d, the whole thing. So this is going to be a half. Hack's exponent is a half for this optimal version. So this gets us back to this boring thing. So, but we can actually check real data. Banavar did this. This is this 1999 Nature paper. And it's clear they hadn't made this connection, that this 3 halves here is 1 plus a half, 1 plus h. Right? What they're saying here, this is d plus 1 over d, so it's little d plus 1 over d, so this is 3 halves. So this showing, and look at that scaling. That is pretty, these are 3 different places. These are smallish networks. They're not continental scale. The smallish ones are decent sizes, but that's a pretty good scaling for 3 halves. So the result for this was, we have this theory that, of course, they get 3/4 and, all this stuff, and it's crazy. But they got this one out, and this is totally correct. Unfortunately, it shows you that basins are isometric, and they are kind of boring, and this hack thing isn't really a big, crazy thing. So the optimal Hack's law is actually, but it's a little more than just dimensional analysis. There's an optimality that we've kind of argued that we can get to that shows, in fact, the dimensional analysis version has an optimal aspect to it. All right, so that was good. And then there's, so it's boring. And then there's, this is another version. This is using the data that I worked on. And so it's now continental scale. And again, this is the 3/2 scaling, and that's pretty good. We should feel happy about that. This is close to 7 orders of magnitude here. And then, of course, this, because this area volume has 10 orders of magnitude this way. Always good, right? Very delicious, yes. You want at least 3 in each dimension. I mean, someone will tweet at you. There'll be someone waiting around with their power law story to tweet at you that this is not right. Probably these days. Anyway, and then there'll be a little tweet rage thing. Okay, so never read the tweets. So this is great. I think this is great. It's totally great. All right. Anyway, let's see. What else have we got? So I published that paper in 2010, and then somehow they got one into PNAS straight away, and it's like a whole bunch of them. And now they're back to like, yes, we have a general basis, right? And then they have things like it's been known for decades, metabolism, but they're saying it's close to 3/4, whatever. But this is one of these papers. God, this is just so crazy. This is number 2. Let's see. It's all connected. This is so great. I know. I might sound crazy. This is James Brown, so that's West Brown and Enquist. The original stuff. Demuth is the one behind Demuth's law, which is the scaling of, it's a beautiful idea that the density of organisms in space scales as mass to the minus something, right? So there are less elephants per square mile than there are mice, and it scales in such a way that the amount of stuff they eat balances out. So it's kind of an equipartitioning thing. It may not, it's not exactly true, but there seems to be roughly, it's like the heartbeat thing, it's sort of roughly true, right? So there are fewer elephants, but they eat more than the mice, of which there are many more, and there's sort of a rough balance. Now, I don't know, maybe that is or isn't true, but it's an interesting thing to think about, like do ecological systems necessarily end up like that? Do they have to end up like that if they're kind of in balance in some way? All right. So fun times, there was that one. Let me fail to get back to where I was. Okay. Okay, here's another fun power law one. We're nearly finished with all this. This is I can't believe this one. So this is Mason Porter. He's a good guy, very quirky, interesting character, who was at Oxford but is now back at UCLA. I think principally because he loves the Dodgers. Anyway. So they published this thing in Science, and they're saying they're just basically like, all these power law things, we're sick of it, right? Stop doing this. They're trying to like send a big story out that you shouldn't claim you have a power law when you don't, blah, blah, blah. And they published what is really an opinion figure, which is an interesting thing to do, right? This is, and there are almost opinion type equations, right? And you could say that about economics. But they convey great certainty. So these are just some points. There's nothing there. They're just some points. This is where your theories are, people. This is a slam. This is the mechanic, our understanding of the mechanism for how these things come about. And so they're saying not good, and then the statistical support for a scaling of whatever it is in this system, not good. They've got 4 out here. They like this one, right? But again, claiming not so much goodness here. And they're actually pointing to West Brown and Enquist. Yeah. So incredibly, it's actually here. I mean, it really is. I'm saying it is. So I wrote to Mason, I said, dude, you don't know about this madness. Because he didn't know, because of that citation history, the way that works, the way this is beautiful and exciting and is talked about. And I know this is true in a lot of areas of science and so on, and it's just weird to be a part of one of them. It's easy not to see all the criticisms. And often there are just crazy criticisms that are wrong. Sure, Anyway, he published something a bit later to say, this isn't, all right, basically that one's not as good as it was. I mean, their general, like, waving flags and being upset remains, I guess, I don't know who Strumpf is, but he didn't want to be part of it. So Porter put something on the archive, and I guess if it's less than a page long, they'll reject it. So he had to maybe add some, he made a blog post or something. Anyway, that was funny. He's an interesting character. But that's an opinion figure, right? I mean, there are no dimensions here. Look at it in science, and I don't understand it. Anyway, there were a couple of replies. Barabazi comes along and says, he actually basically used the same thing. Every 5 years, someone comes along and says this, the same thing he said to Clauset, and says power laws and blah, 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 blah. And, yeah. Anyway, really, that was so weird. Oh, my God. I think it was, I'm pretty sure Morgan Frank showed me this. Yeah, and you should ask Danforth and Frank how I explained, how I reacted at the time. Wow. What is it? Yeah. Yeah. I mean, this is still, this at some point has to be something that's like quantified, right? I mean, at some point this has to be a thing, a number, but it's still this is clearly an opinion at this point, no? Yeah, I mean, we could come up for units, right? I mean, I don't know. All right, so the summary for this whole thing is, basically dimensional analysis actually works out, but it's bigger than just dimensional analysis. You can supply these isometrically growing ones more efficiently. Kind of makes sense. That seems okay, right? You don't have to, the volume of the network doesn't have to grow that fast. Is that right? Am I telling lies? Maybe I'm telling lies. But anyway, yeah, so the ambient thing matters, right? So there's a big difference between, for the blood network story, which is really 3 equals 3, and 3 is greater than 2 for the river network one, which are physical examples of something that's more abstract. If we get away from this kind of optimal scaling, then maybe we have some kind of inefficiency. I mean, that's the thing. No one ever really says this, but if it's 3/4 or it's higher than 2/3, then that's not great. You seem to be what's going on? Why are we using more stuff? We don't seem to use it for our brains very much. 20 watts, 30 watts. I mean, that's not a lot. As is in evidence, pretty much everywhere in the world, but except for squirrels. Really good. They get some good stuff out of that little brain. Right? Just geniuses. Okay. I really, every time I think about scaling of brains, the koala thing is just sitting there as like a side note of despair. I mean, this tiny, smooth brain. So bad. Okay. Okay, all right. So, and the details of branching networks aren't that important. I think that makes sense too. You have an algorithm for building these things, particularly in biological ones. You want to grow, and angiogenesis means you're just sort of working to build a network that will supply everything. Doesn't have to branch too fast or too slow. It's going to work. Self-similarity will vary as a result, but the algorithm of a self-similar kind of algorithm, an algorithm that produces self-similar structures, is an easy algorithm to construct from evolution. Right? Evolution can kind of come up with, we're going to branch. And we have that in phyllotaxis, which is a whole thing I haven't put in here, right? Which is the growth of trees, and we get the Fibonacci number sequences and things like that. Pine cones, and they have beautiful story. I should put that in. Okay. But I mean, you can see again, that's let's have, there are all the horrible biological details, but basically there's it boils down to this sort of simple budding algorithm that's, it's not making some crazy decision every time. It's just I'm going to make another one, I'm going to make another one, and that gives rise to, the whorls you see on pineapples and things like that, which is cool. Right, so the exact details won't matter, but just that it is a scaling thing is important. So 2/3 around, it still gets abused. Yeah, All right. It really is amazing. It really is amazing. So, I mean, years ago, I talked to this, I think I mentioned this, right? I talked to a journalist at Nature who was writing about it. It's 1998, and I said, someone should write a book about this. This is a really interesting history of science thing. And that's where, that was, so that guy did write a book, but it was not the right book. It says, this thing is awesome. And you can see the beautiful story, right? Huge mystery of nature, mechanistic explanation. And I will say that this is actually something I said. We have a mechanism. Like when there was criticism, they say, we have a mechanism for how it works. And it's like, and you don't, or no one else does. So, and that's good. It was good to have a mechanism, but it's not right. Anyway, I was looking at this too. There's a lot of madness back here. Oh, look at all that good stuff. There you go. And that's just a sample of the craziness. All right, I think I've done that to death. There's more, but that should be enough. All right? Do you feel like we should talk about something else? I guess so.